Hello wonderful person, this is Anton, and in this video we're going to be talking about the beautiful Jupiter. In one of the recent studies that I was able to discover completely by accident, we discovered that maybe, just maybe, we were not really correct about the origin of this planet. It seems that the study from University of Lund, which is in Sweden I believe, actually found out that this planet was made in an entirely different way from what we expected. So let's talk about this, and welcome to What the Math. So our previous assumption about this planet is that it was made somewhere where it's located right now, maybe a little bit closer to the Sun. And the way that we believe Jupiter moved in our solar system, and this is by the way known as the Grand Tack theory, basically we thought that it kind of got attracted to the inner solar system and made its way closer and closer to the Sun, stopping somewhere around where Mars is located. Then, because it was so close to the other objects that were here, it influenced a lot of planets, and some of them collided with each other. And then its friend Saturn decided to pull a little bit more on its neighbor and managed to pull Jupiter all the way back to where it is located now, at a distance of just over 5 astronomical units. So that's how we believe Jupiter was made. But the only problem with this particular hypothesis is that we don't really have any actual substantial proof or really any evidence of this happening. So we're kind of left with just kind of guessing as to where Jupiter came from. But this particular study that you can find in the description below talks about something entirely different, and they kind of give us proof as well. So what they did is they actually created simulations, specifically very complex computer models that they ran many times, where they placed Jupiter in different locations around the solar system. But they weren't really interested in Jupiter. They were actually trying to figure out why Jupiter has such an unusual number of so-called Trojans. And not just an unusual number, but different number of Trojans. Okay, so first of all, let's briefly talk about what Trojans are. You can actually see me selecting some of them, but obviously not all of them. So, first of all, Jupiter, just like every other object in the solar system, has several stable points of orbit known as the Lagrange points. There's one that's very popular with different spacecrafts. We actually have a bunch of them between Earth and the Sun. This is called L1. But there's also two Lagrange points, L4 and L5, that are sort of about 60 degrees, this is basically 60 degrees, in front of the orbit and 60 degrees behind. Now, this is known as the leading Trojans, and this is known as the following Trojans. And Jupiter has a lot of these asteroids that it was able to capture over the 4.5 billion years in these particular points. There's about 7,200 of them that we've discovered so far. And it just so happens that for some unusual reason, there is about 40 to 100% more of them here in front of Jupiter than there is behind. And this is where the mystery sort of begins. We were never actually able to explain why the so-called Greek camp, as it's also known, has a lot more Trojans than the so-called Trojan camp. This is actually kind of named after the Trojan War. Now, there is, like I said, about 100, possibly 100% more of Trojans here than here. And this mystery was never really explained. We kind of just have taken it for granted almost. Until this particular research actually did simulations where they placed Jupiter in different locations of the solar system and then had it kind of travel around and basically explore the solar system for various reasons, until they managed to simulate this exact scenario. They actually placed Jupiter in just the right point, and as it migrated to its current location, it captured about the same amount of so-called L4 Trojans and L5 Trojans. Now, this is where it gets interesting. The location where Jupiter started was entirely different from what we believed. It actually started its migration from the region very close to where Neptune is today, approximately 18 astronomical units away from the Sun. And this is kind of unexpected. It is somewhat more logical in a sense, because this is where you would expect for all of the gas giants to form, at the farther reaches of solar system, where there's a lot more ices and a lot more gas. near the sun, there's not a lot of stuff that was left when the sun became basically sun, when it became active. It most likely threw away a lot of this material onto the outskirts. And then once Jupiter was formed, it started migrating toward the solar system. Basically, it started changing its orbit relatively quick. This only probably took it about 700,000 years. And as it migrated, it started capturing all of these rocks. And then at a distance of about 5.2 astronomical units, it stopped. Although maybe it actually hasn't stopped completely just yet. And by then, it captured all of these Trojans that it has today. And it just so happens that there's so many of them here that if these Trojans were actually captured from basically the entire solar system as Jupiter was migrating toward the sun, it would actually allow us to study pretty much the entire history of the solar system in, well, one relatively easy to access spot, because it seems that these rocks are primordial pieces of the solar system that never really became planets. And because Jupiter traveled so much through the solar system, and because a lot of these Trojans are actually quite different from each other, it would allow us to kind of combine all of them into one long historical account that could actually potentially explain the creation of the solar system in a lot of detail. And guess what? NASA decided that it actually wants to launch a mission here. In 2021, NASA is going to be launching a mission known as Lucy that's going to do just that. It's actually going to go to Jupiter's Trojans and visit both of the camps, the so-called Greek camp and the Trojan camp. Here's actually what the path will look like. So this is basically 2021, we'll launch the probe. It then goes to the L4 Trojans first. It explores 4 different locations. This will only be in about maybe 2025, mid-2025 until approximately 2028. And then it's going to take a few more years to go to the other side, where it's going to study the L5 Trojans. The entire mission will take approximately 12 years, so by then, yeah, most of us will be pretty old, but nevertheless, it will actually allow us to understand the creation of the solar system with a lot more detail. And because we get to visit all of these objects and also study them in somewhat accurate detail, it even gets to visit a binary Trojan at some point, we'll actually get to learn quite a lot about pretty much everything in our solar system. Now, this is the binary object known as Patroclus that is going to visit last, and if you look really closely, you'll see that it has a partner right there. It's kind of difficult to see from this angle, but a lot easier to see from this perspective. So we'll get to visit all of these, study them in quite a lot of detail, and hopefully understand the creation of the solar system once and for all. Now, for now, all we can kind of do is, I guess, wait, but also hopefully future studies will actually run a few more simulations and trying to understand if this actually makes sense, because this, in a sense, means that Jupiter, on its way through the solar system, was able to collect quite a lot of data. It literally collected all of these pieces as it moved through the entire solar system and sort of had them stuck in the same region of space known as the Lagrange points. I mean, technically this makes Jupiter a great collector of scientific data that may have helped us solve all of the mysteries all in one place. We just have to go to these Trojan points, or Lagrange points that is, and study those Trojans in a lot more detail. But like I said, if this particular hypothesis is correct, this may mean that we're kind of now unable to explain the creation of Earth again. But this also means that we may have been wrong to begin with. On the other hand, this is kind of how science works, and one day we'll be able to answer all of these questions with certainty, but for now we can, I guess, only keep studying and watching and launching all of these wonderful missions like Lucy, hoping to discover the truth. Hello wonderful person, this is Anton, and in this video we're going to be talking about something unusual that was recently observed by amateur astronomers when looking at Jupiter. It's something that happens quite a lot, but nevertheless surprises us every time. And let's begin by looking at what was actually seen. So this is from Ethan Chappell on Twitter, and you'll see it in a few seconds right here. There's a little white spot that suddenly occurs on the surface of Jupiter. Now, can you guess what this is? You probably can. It was basically a collision with Jupiter that was observable and visible from really far away. Here's a slightly easier way of seeing this. This is the image created by Étienne Chapelle himself. So what we've observed is actually not very uncommon, even though it is quite impressive and quite interesting. But before I tell you what may have collided with Jupiter, let's talk about some of the more famous examples of collisions with this beautiful planet. And it just so happens that we even have this simulated in Universe Sandbox. It's a pre-made simulation that shows us what happened back in 1994. You may see the date on the bottom there. So this is something that was super exciting back in 94 because a lot of scientists were observing Jupiter at that time and making a lot of really interesting predictions. You might remember what happened if you were around back then, and if you don't, well, basically it was a collision with a comet that broke apart, and it had several pieces that collided over several days. This was the comet discovered in 92, known as Shoemaker Levi, named after the discoverers, and as you can see in this actual photo, it was basically like a little train of cometary pieces, anywhere from a few hundred meters up to about almost 2 kilometers in size. Now, even though technically it doesn't sound like a really large comet, it ended up producing some really spectacular things on the surface of Jupiter. And even though these scientists tried to predict what's going to happen to Jupiter, they really didn't know. So there was a lot of really interesting observations conducted here. And here's one done in infrared. You'll see that the explosions that happened on the surface were actually really powerful and created a lot of heat. And this heat was so strong that it was visible for several weeks afterwards. The temperatures here were close to about 24,000 degrees Celsius, which is basically a pretty hot environment. And considering that these fragments, despite their small size, were able to produce formations that were basically size of planet Earth or even larger than that, it does kind of make you wonder what would happen if these collided with our planet. So this is actually a kind of a realistic representation of what happened on Jupiter. The actual fireball that was produced, that was really hot, created these beautiful waves that propagated across the surface of Jupiter at a speed of about 500 meters per second, and you could actually even see them move across Jupiter in several different spots. And what's really interesting about each of these collisions is that they all left these very interesting dark spots on the surface that were composed of different materials from those comets, or from the cometary pieces. And they actually stayed on Jupiter for several months. You could easily observe them with a relatively small telescope, and these were even more easily visible than the Great Red Spot of Jupiter. So each of these spots that was created, which we're going to do right now as well, stayed there for a long time, was very visible, and generated a lot of energy. Now, remember, the original comet we think was only about maybe 2 kilometers in size. Just to give you an idea, here's what the Halley's Comet, one of the more famous comets, looks like. This is at least double the size of that smaller comet that collided with Jupiter. So an object that's only this big generated a tremendous amount of energy and very visible effects on a huge planet like Jupiter. So let's just maybe finish these collisions. You'll see how each of these cometary collisions will leave a very interesting mark on the surface. And so all of this left Jupiter with roughly around 21 different marks on the surface. In total, it was something like 6 million megatons of energy that was released, which is roughly around 120,000 times less than the super famous Tsar Bomba, the biggest nuclear weapon ever detonated. So this is kind of what Jupiter had for a while, and after a few months, everything went back to normal and these spots disappeared. But the interesting thing is that these spots were formed by the material from those comets, so we could actually study what's inside of them and discover the composition of these comets. And that's because the comets never really reached the lower levels of Jupiter. All of them sort of disintegrated and exploded much before they reached even the water level of Jupiter. All of this happened at a really high velocity of roughly around 60 kilometers per second, and because of this, the entire comet basically just exploded in the upper atmosphere before it reached even 2 atmospheres of pressure. By the time it reached 3 atmospheres of pressure, it was basically already kind of gone. And so this is something that's pretty common on Jupiter. Today we believe that roughly around 2,000 to maybe even 8,000 more collisions happen on Jupiter than they do on Earth. And that's really important because it makes Jupiter I guess you can call it a vacuum cleaner. It's literally the solar system's vacuum cleaner that sort of collects all of these comets and all of these asteroids that would come to Earth otherwise, and has them collide here instead of colliding with our planet. Many scientists today believe that because of Jupiter, the complex life was able to evolve on planet Earth, and that without this beautiful giant, we would probably never have a chance to evolve to the point where we are today. But that's not really what this video is about today. Today, I wanted to briefly talk about what was observed by Ethan Chappell right here. So we know that this was a pretty powerful explosion as well. As a matter of fact, it's almost size of Earth. It's a huge explosion. It's several thousand kilometers across. But as you can see, it only lasted for maybe 2 seconds, 3 seconds maximum, and then sort of disappeared. The only reason Ethan Chappell was even able to see it is because he had some sort of a software running that was meant to detect these flashes and explosions. And so this here is actually something that happens quite often and is caused not by a large comet like you just saw with Shoemaker Levi, but something much smaller. As a matter of fact, we think that this rock here was probably only about 10 meters across. And that's really mind-blowing. It's a much smaller mass, it's a much smaller rock, but it's able to produce an actual flash pretty much comparable to the flashes we saw with Shoemaker Levi. And that's of course because these are the explosions that happen initially when a super fast object reaches the upper atmosphere and generates a tremendous amount of energy that generates an explosion. It's what we would call an air bolide. And today we're pretty certain that a very similar impact occurred back in 2010 and another one in 2012, because we saw a very similar flash to this and it only lasted for 2 seconds. And one major difference between this flash and the ones from Shoemaker Levi is that after we looked at it again, the surface of Jupiter did not have these very distinct patterns that were formed by the material from the comet or from the asteroid. This was seen back in 2009 though, when an object that was roughly around 500 meters collided and left this mark that you see here. So a larger asteroid would produce this, but a smaller rock that's only about 10 to 20 meters would just explode in the upper atmosphere and would most likely leave no mark. And so this is how we can distinguish what collided with Jupiter. But these smaller collisions happen very often. As a matter of fact, we've always tried to kind of understand how exactly the moons of Jupiter, like for example Ganymede, got these unusual formations. Now you can imagine how they actually formed. This was created by another similar object, possibly a comet, that approached Jupiter, and when it came too close to the planet, because of the tidal forces and the gravitational stretching, it fell apart and created this kind of a line that you see here, formed by the fragments of the comet or the asteroid. And eventually, just like back in 1994, this whole train of comets or asteroids collided with Ganymede, collided with Callisto and other moons of Jupiter to form these unusual patterns that we can now explain pretty easily. So this is just another example of how often these collisions on Jupiter do occur. Although we think that the bigger ones like Shoemaker Levi only happen maybe every few thousand years, these smaller collisions happen pretty regularly, with small rocks like one we just witnessed happening possibly every year, several times a year. And because so many astronomers have been looking at Jupiter to try to find more of these flashes, we've been able to discover quite a lot of them in the last few years. But I guess the most important takeaway here is that Jupiter is exceptionally important for protection of life here on Earth, and these collisions happen so frequently that without this beautiful planet, we would have probably been gone long time ago. It literally sucks in everything from the outer solar system. It's able to influence many different asteroids and comets and sort of bring them closer to itself, and those comets then fall into the planet here instead of falling on a much more fragile planet Earth, just like you're about to see right here. Now, the collision with a comet right now would have probably have such a devastating effect that it would literally wipe out pretty much all of the major complex life on the planet. Just like another comet did 65 million years ago when it collided with our planet right here, and caused the destruction of pretty much all major dinosaur species on the planet. So comets do cause major trouble for us, and we need to make sure we're able to somehow divert them if they decide to come too close to our planet. Hello wonderful person, this is Anton, and in this video we're going to be talking about a new discovery coming from right here, our neighbor Jupiter. In this video we're going to discuss the potential very large collision that this planet experienced billions of years ago, early in the creation of the solar system. So our story starts right here around Jupiter. A few years ago we launched the mission known as Juno that I'm trying to select right here. This is, by the way, using the free software directly from NASA known as Eyes on the Solar System. You can easily find this on NASA's websites. So this right here is the Juno mission. I've talked about the mission itself previously. It's probably most famous for using these solar panels really far away from the sun. And here we only get about 2% of the efficiency when it comes to solar panels compared to our own planet Earth. But anyway, so as this beautiful probe was orbiting around the most massive planet in the solar system, which is Jupiter, which is somewhere right there far away, it started to discover a few things that we couldn't really explain. Now there are a lot of really exciting discoveries that have already been very thoroughly analyzed by the mission. Like for example, we already have a very clear picture of the aurora on Jupiter's surface, and you can kind of even discover them by using this free application. We also have analyzed the magnetosphere of Jupiter very accurately. You can also see what all of this looks like in Eyes on Solar System. We even have a very accurate representation of the radiation field around Jupiter, as you can see. And lastly, we also have a more detailed picture of the rings that are kind of barely visible because they're really small compared to the rings of Saturn. But the more exciting news coming about Jupiter is actually coming from the inside of the planet. Because by studying the inner core of Jupiter, we started to discover something a little bit unusual. The core of Jupiter that you see right here doesn't seem to be as solid and as structured as we assumed it to be. It seems to be more dilute and a lot more spread out across the entire volume, as if something disturbed it. Now, this wasn't really very clear to us. We couldn't really understand why this is so. And we're actually still not even sure. There are possibly a lot of other explanations. But in this video, we're talking about one of such potential explanations. That's probably also one of the more exciting ones. And you could probably already tell from the title that it's about a collision with a very large planetary object. Basically, a collision with another planet. And although generally scientists today believe that planetary collisions are actually super rare. They only happen like maybe once every few billion years, and a chance of having a large collision with Jupiter, according to some of the scientists, is like 1 in 1 trillion. It's super unlikely. Nevertheless, for this particular paper, the scientists estimate that within the first few million years of the existence of the solar system, because of the amount of various planetary objects in the solar system, and because of the sheer gravitational attraction of Jupiter, the chance for collision was not so low. It was about 40%, or basically 40% chance that Jupiter did collide with something. And this is how the scientists behind this paper from Nature magazine try to describe and explain what we're seeing inside the core of Jupiter and why they think it's so diluted and so unusual. They believe that some sort of an object, a very large object, collided with Jupiter pretty much head-on and changed the core composition and also core structure itself, eventually turning the core into this very large, very diluted structure that we have today, that even after 4.5 billion years still hasn't really solidified into a solid structure. In other words, this collision was so dramatic and so huge in proportions that it completely restructured the inside of Jupiter. But this wasn't a simple collision similar to the one that Earth experienced when the Moon was created. Here, if for example we take an object, like let's just say something equivalent to Uranus in size, and then try to launch it at Jupiter, but here under an angle, you'll notice that as it collides with Jupiter, which is kind of what most of collisions we think are like, it would most likely only affect the outer regions of Jupiter. It would never really make it to the core, and all of the material that's going to be generated here is very likely just going to disturb the outer surface. Let's see what actually happens. I'm kind of curious what will happen in a few hours here. but it's not going to affect the core. So we think that this is not the type of a collision that happened here. This collision would not really change the core almost at all. On the other hand, a collision with a planet that's a little bit more similar to Earth or a super Earth, so anywhere from, let's just say, half a mass of Earth to about maybe 4 or 5 masses of Earth, would not really provide enough effect to affect Jupiter as well. It would most likely, let's see what actually happens again, it would most likely not really pierce through the thick layer of Jupiter, and thus would not really affect the core as much either. So here, after all of this explosion settles, it would probably leave something on the surface here and would maybe go through a couple of thousand kilometers of the atmospheric layer, but it very unlikely would pierce through the atmosphere or ever get to the core at all. And so once again, we believe that a collision with a smaller object would only affect the upper atmosphere of Jupiter, not so much the core. So a very unique type of a collision with a very specific angle and basically a very specific mass would have to have occurred to generate the effects that we observe inside the Jupiter's core. And what do these scientists think happened? And according to them, as Jupiter was orbiting the solar system, and here you can see it flying through the solar system, it received a head-on collision from a planet that was roughly around 10 masses of Earth in mass. So maybe a little bit less massive than Neptune and Uranus, a lot more massive than Earth, and also very similar to objects that we usually refer to as sub-Neptunes. So here, if we try to simulate this collision is going to happen head-on at a very, very high velocity. We believe that there were many such planets in the early solar system. We also believe that these planets were very likely responsible for colliding and possibly even producing some other planets like Earth and Mars. But most importantly, today we believe that one such planet still exists, and this is something I'm going to talk about in a few seconds after we see what happened to Jupiter when it experienced this collision. So this would very, very likely reshape the core of Jupiter, making it more diluted, but also because it's a head-on collision with such a massive object, it would also cause Jupiter to migrate. It would very likely change the orbital speed of Jupiter, decreasing it, thus making Jupiter move to a different location in its orbit. Now, planetary migration is something we believe happened many billions of years ago, but this could have been the start of that migration. If something suddenly shifted Jupiter in its orbit, it would then start shifting all other planets, including, for example, Mars and Earth and of course Saturn. So all of this could have started with this really massive collision that then influenced Jupiter's insides, and this is what we're observing. Now this is still a hypothesis, it's not a theory, and it definitely needs a follow-up study and a lot of other observation and possibly even more proof, but for now it does make a lot of sense. There is, however, another really important idea that all of this proposes. The idea is of having such a very massive planet in the existence of an early solar system, which of course gives more credence to the theory of Planet 9, because it is very likely that some of these planets did collide with Jupiter, but some of them, possibly even from the same planetary body formation region as the one that collided with Jupiter, may have approached Jupiter too close, and as a result of this, as a result of a gravitational interaction, got kicked out of this inner solar system and ended up moving all the way to the back of the solar system, where it then stabilized and is there today. In other words, this sort of provides a little bit more proof to the existence of Planet 9 and how it could have ended up in the far regions of the solar system. Now, for now, we don't really know if Planet 9 is real, we also don't really know if Jupiter received the collision, but both ideas do kind of come really nicely together, especially if we do discover that Jupiter received the collision, or if we discover Planet 9 somewhere out there. For now though, we don't really yet know if any of this is a fact, we just know that it's very possible. And this is the brilliance of science. We need to test and double test, and people need to try to disprove the theory before it becomes a fact. Hello wonderful person, this is Anton, and in this video we're going to be answering a question that was posed by one of the wonderful Patreons I have. And this is from a person named Ralph, who was wondering, so okay, hypothetically, if our solar system's habitable zone has expanded further and further to the area where Saturn and Jupiter are, or even further than that, would these gas giants, like Jupiter that you see in the back there, evaporate because, you know, they're gas giants, and would objects like Europa, Ganymede, Titan, and so on, would they actually turn into planetary objects? Or in other words, planets. And I think to try to simulate this at first, we can imagine that one day this actually is going to happen, because our sun one day will start turning into what's known as a red giant. Its mass will remain the same for the most part, it will actually even decrease a little bit, but it's going to start growing because it's going to run out of hydrogen and helium, and the forces on the inside will start making it grow in size. So at some point, the actual habitable zone that you see in green will reach Saturn and Jupiter, but then we'll also go further and further. Our sun is going to get so big that it's going to first swallow Mercury, then it's going to swallow Venus, and then possibly even Earth. Mars may survive, but we're not really sure yet. At that point though, the habitable zone is going to be really far away, probably past Pluto. The estimates right now suggest distances of about 40 to 70 astronomical units, so objects in this vicinity, for example, all of these dwarf planets like Eris and Sedna, potentially might turn quite habitable. They'll probably become somewhat habitable looking water worlds with quite a lot of liquid water on the surface. But that's not really what we're talking about. What will happen to gas giants? What's going to happen to all of the objects orbiting them as well? Well, let's start with Saturn. So the thing about gas giants is that they've already collected all of this material, they've already collected all of the gases and all of the so-called ices like water and methane, so they're not going to go anywhere. These objects are not going to suddenly evaporate and disappear. And that's because they've already collected so much mass that they can easily hold on to all of the hydrogen, helium, and so on without really any problems. So even being so close to the actual sun and being illuminated by so much extra radiation will not really change their mass that much. They might increase evaporation a little bit, but they're not going to suddenly disappear or possibly disappear at all. They will, however, turn much hotter. So the estimate for example, Saturn right now is approximately 300 degrees Celsius, so it's going to become what's known as a hot Jupiter. It's a type of a planet that we've discovered in a lot of different star systems, where depending on the distance to the parent star, the actual planet becomes really hot, but it doesn't really disappear. Some of them do come really close to the parent star, like for example, let's take Jupiter, that's even closer and whose temperature right now is close to about 500 degrees Celsius, and then place it even closer. Let's place it at a distance of about 1.5 astronomical units so that its temperature increases even more. It's not going to start kind of burning and will start losing more material, but still not enough to disappear anytime soon. Many of these planets actually do eventually disappear and leave behind the scorched cores, the actual hard core that's inside the planet, if they have one. And these are often known as Chtonian planets. I've made a few videos about this concept in one of the previous videos that you can probably find somewhere above my head right now. But for the most part, they actually still don't really change that much, especially if these objects are really massive. They can easily hold on to hydrogen and helium, and the sun itself will not really affect them that much, but it will change what's happening on the surface. So one major change that both Saturn and Jupiter will have is that their atmospheric conditions will start being even more extreme. And although currently it already seems to have quite a lot of storms and all kinds of hurricane-looking conditions on the surface, it's going to increase dramatically. Like, this whole planet is going to be covered with tremendous amount of winds and all kinds of wind-related activity, and the actual speed of the atmosphere may increase dramatically as well. The cloud patterns will also change dramatically. We don't really know how, but we know that it's going to be very different because it's going to be much hotter now. But one of the biggest sort of changes is going to be related to the sudden increase in all sorts of charged particles that are going to be hitting this planet. And the way that it's going to reflect is by quite dramatically increasing the size and the power of the aurora effects that are present in the atmosphere of both Saturn and Jupiter. So these are going to be really extreme. the entire planet will probably be covered in these effects and they will be visible from really far away. And this is all because the sun itself will become dramatically more active. It's going to have a lot of so-called coronal mass ejections that are going to be so powerful that the planets will probably just be lit up with all sorts of colors coming from those aurora. Now, because we currently don't have anything like this in our solar system, we can't even imagine how all of this will look like, because right now the most powerful of these aurora are technically around Jupiter, and Jupiter is still pretty far away from the sun. But luckily Space Engine allows us to recreate this a little bit, and for all we know, maybe this is kind of what it's going to look like for at least one of these planets. Although it's possible that the extra radiation coming from the sun might somehow disrupt the composition of the upper atmosphere, for the most part, the planet itself might not really change that much, although the color of the planet and the appearance of the planet will probably change quite dramatically. Now, what about moons of these objects, specifically moons of Saturn and Jupiter? Well, every moon that's currently made out of ice will obviously melt and lose a lot of this water over time because they're not going to have as much protection from the solar activity. And so even though technically for at least a few million years Titan will probably have liquid water, at some point even all of this will eventually evaporate, leaving behind an empty shell, possibly a tiny rock actually. And this is because, well, first of all, the temperatures here are going to be really high. Right now the temperature is showing at 300 degrees Celsius. This will definitely evaporate all of the water and all of the other gases here, and because it's technically going to be kind of like a small gas object, all of this gas will eventually escape and either combine with the parent planet, in this case of course the parent being Saturn, or it's possible that it's going to escape into the outer solar system and, well, nothing else will remain here, except for whatever rocky substance it might contain on the inside. We don't really know if it has any core, but if it does, it's going to stay behind as a kind of a tiny reminder of what used to be here. All of the other objects will have very similar fate, and so the planet Saturn will probably lose most of its moons because a lot of the moons here are ice-based. And none of them will turn into planets because it's going to be really hot here. However, with objects like Neptune and Uranus, things might get a little bit more interesting, specifically in Neptune because it's the farthest planet here. First of all, neither of these objects will be affected in pretty much any way. They're just too far away from the sun, even though it's so gigantic now. But technically speaking, the moon Triton here would be very interesting because it might potentially become a very interesting habitable water world. However, the problem with Triton is that because it's currently orbiting in such a weird way, it's actually slowly approaching the planet. And by that time, it will most likely collide with Neptune. It will probably not exist anymore. So if somehow it manages to survive in about 5 billion years from now, it might turn into a relatively comfortable looking water world with potentially even some atmosphere. But due to the fact that it's way smaller than even our moon, and also because it's most likely similar in composition to Pluto, so it's essentially all ices, it's not going to have any surface to stand on, so it's going to be just a liquid water world. But all of the other objects here may kind of still stay in the same place and not really disappear anywhere because they're just too far away from the sun. It's not really going to affect them as much. And neither Neptune nor Uranus are going to experience any major changes. So all in all, it's going to be a very different solar system from what we know today, and this particular period will probably last for just under 1 billion years. And after this, well, that's going to be the end of most of life in the solar system if it still exists here. And that's because our sun is going to release all of this mass here, well, most of the mass, and create a beautiful phenomenon known as planetary nebula. This is going to be our sun. It's going to be a white dwarf, the core of our star in the middle, and the rest of the stuff is going to be the leftover star material. And all of this material, as it escapes the solar system, is going to, well, literally scorch our planets, probably stripping them of everything, and leaving very little behind. Now, we don't really know how powerful it's going to be and if there's going to be anything left, but life cannot possibly survive these events. It's going to be very difficult. Unless, of course, we advance to the point where we can actually control this and somehow avoid this. And following this, that's all that's going to be left. The white dwarf known as the Sun, with a few leftover materials, like for example these rings that used to be planets, used to be actual objects, but now are just the debris and the leftovers from what used to be. So that's going to be the end of our solar system, and that's based on the fact that we've observed these around other white dwarfs out there in our galaxy. And obviously we don't know if all of the stars follow the same sort of path, and if they all end up with the ring system, and if they all end up losing all of their planets, but so far that's kind of what we've seen. And although there might be some other leftovers, like tiny objects that resemble planets, all of the planets that we have today are probably going to be gone. Okay, so today we know that life does not need oxygen to survive. As a matter of fact, life on Earth started when there was practically no oxygen on the planet at all. And even though the earliest Earth probably looked something like this, it didn't really take long for Earth to look slightly different. And we know all of this because we've discovered some of the most ancient life on Earth right here in Australia. These fossils that are practically several billion years old suggest to us that life back then was very different, and the atmosphere of Earth was also very different as well. As a matter of fact, if we actually look at the history of our planet from the geological perspective, today we know, for example, that up until about 2.3 billion years ago, most of the atmosphere on our planet Earth was actually not really rich in oxygen, so most of life on Earth had to rely on something completely different, most likely CO2 and possibly even hydrogen. Then about 2.3 billion years ago, the event known as Great Oxygenation Event completely transformed the atmosphere of our planet, turning it into the world we know today. At the same time, this is probably the first time that the Earth actually turned into so-called ice ball Earth, and all of this was because the CO2 levels fell dramatically, oxygen was pretty much everywhere, and the planet was suddenly very, very cold. But the life on Earth did start when the Earth itself did not have oxygen and most of the atmosphere was entirely different. And a lot of these ancient bacteria even today proliferate in areas where there is no oxygen, like for example, inside of you and me. Basically, in our guts there is quite a lot of bacteria that survive quite well without any oxygen. So this is something we know for a fact. And so this is exactly why the scientists behind this paper decided to conduct the experiment and find out if the modern life, basically bacteria that we currently have today, would be able to survive in more extreme conditions with atmosphere entirely different from the atmosphere of Earth today. The main purpose of this experiment was to actually see if maybe we should be focusing on looking for life in planets that don't actually have similar conditions to Earth, including of course some of the planets we currently have in the solar system. And so the scientists behind this paper created this relatively simple experiment. They took E. coli, which is practically the most studied bacterium on the planet, this is the most well-known bacterium to us, and also common yeast, and decided to place them in essentially atmospheric conditions different from planet Earth. And in simpler terms, they took the bacterium and the yeast and they placed them into conditions of, for example, enriched nitrogen and CO2, like in this case, and then watched this bacterium grow and spread across the entire culture. They did this for several different atmospheric conditions, including the atmosphere entirely composed of hydrogen and entirely composed of helium, just to see how these little guys would be able to handle these different environmental conditions. And as you can probably imagine, it went really well. They even created this relatively simple summary of everything they've achieved, and essentially, for the most part, both E. coli and the yeast were able to grow in hydrogen conditions just as well, or almost as well, as they did in typical oxygenated environment. Basically, for bacteria and yeast, it does not matter what the actual atmosphere is made out of as long as it's not toxic. And since hydrogen, nitrogen, CO2 and helium are not toxic gases, all of the bacteria were totally fine living in these conditions, also meaning that as long as you give them enough food and as long as you provide nutrition for them, they'll be able to survive around any planet in any atmospheric conditions out there. And although this is definitely not a surprising discovery, what is surprising here is how well the bacterium and the yeast were able to grow in these very foreign conditions, and what all of this means for the discovery of alien life somewhere out there. First of all, this of course means that a typical object like this, Kepler-62e, basically a typical super-Earth that we think may have a lot of hydrogen on the surface and possibly even other gases, but probably not oxygen, would still be a perfectly good place for us to look for alien life, at least bacterial life, which seems to be totally fine surviving in these conditions. In other words, the discovery of life should not be limited to planets with oxygen, even though the signs of oxygen are probably going to be the first locations we look at when we are trying to find some kind of foreign life. But what's even more exciting about this discovery is that we could probably find life similar to life on early Earth, and obviously life similar to the ones you find inside of us, around objects that are not so foreign to our solar system. Basically, we're talking about objects in our solar system. Which objects do you know that have a lot of hydrogen in them? And what objects can you think of that may have displayed signs of potential unexplained phenomena when it comes to life? And one of them is actually right there. This is, of course, Saturn. Saturn and Jupiter are filled with hydrogen and are obviously filled with a lot of other stuff on the inside, including very Earth-like conditions. As a matter of fact, if you were to go inside of Saturn, or even inside Jupiter, you would actually discover conditions not so foreign to us. There's maybe a little bit more pressure, but the temperatures and the fact that there's actually water clouds here, and even things like methane clouds and a lot of other stuff that technically can easily be used by bacteria for, well, essentially food, does suggest that we might be able to find life around these planets as well, or basically inside of their atmosphere. And even though right now I'm just speculating, but this study itself provides enough reasons for us to actually try to look for life a little bit closer to home, around objects like Saturn and Jupiter, specifically in their atmosphere. Although here things will get a little bit more difficult, mostly because it's basically almost impossible for us to reach these locations without completely destroying the actual probe. And we know this because we did this back in 2003 when the so-called Galileo probe, after about 14 years in space, ended its mission by essentially entering the upper atmosphere of Jupiter while being completely destroyed by the, well, combination of high speed, re-entry speed, and also very thick atmosphere of the planet. Here the speed was about 48 kilometers per second. So unfortunately the probe only got to measure some of the components of the upper atmosphere. It never really got to the part where we could have potentially found life. And one of the reasons why the probe was destroyed in this way was to essentially eliminate any chance of the probe itself contaminating the moons of Jupiter. But what the scientists back then didn't really kind of think about is, well, what if it contaminates the planet itself? And the idea here was that, I guess, the heat would technically kill any of the bacteria and prevent this from happening. But you never know. For all we know, if there was no life on Jupiter, maybe there is now, because some of the bacteria could have survived the actual passage through the atmosphere. Either way, what the findings from this study suggest is that life could be present everywhere, at least simple life, bacterial life, the single-celled life that was present everywhere on Earth for billions of years. We are still not sure if we're going to find any complex life out there, but discovering simple life should not really be a problem as long as we know what to look for. The chances of discovering bacterial life are increasing with every single study we conduct, so it shouldn't really be a surprise if we find it sometime in the next decade or so. Although the real question in the future is going to be, did we find life that was originated from that particular location, or did we just find life from Earth that somehow managed to get to those locations, like for example Jupiter and Saturn, because we did send a lot of probes that could have been contaminated. But hopefully we'll get to ask these exciting questions sometime soon. It's been quite a while since we discovered something really amazing about various planets in our solar system, and hopefully we do discover something incredible about them in not so distant future, which will give us more reasons to come back both to Saturn and Jupiter and to possibly even create a colony somewhere around them. And hopefully this location is going to be my favorite moon, Titan. But anyway, we'll talk more about discoveries coming from Titan and other similar moons in one of the future videos, but for now that's really it. It's a pretty exciting study. It does mean that life survives in other atmospheres quite easily, and it does suggest that life could be hiding right in front of our noses around Jupiter and Saturn as well. Hello wonderful person, this is Anton, and in today's video we're actually going to be talking about the Asteroid Belt, and we're going to be talking about a planet that we thought existed in this region that was then destroyed and creating the Asteroid Belt, and this planet had a name Phaeton. So this right here is Phaeton. This is a planet that we thought actually did exist at some point in this region, and then something happened to it and it created the Asteroid Belt. At least this was the major theory for a very, very long time, since basically early 1800s. Back then, scientists actually thought that there was a pattern between the distance between planets and the sun. And so, for example, if you were to look at the distances here, there's actually a kind of a symmetry in terms of distances. And this symmetry can be established as a kind of a pattern. And using this pattern, which I'm going to be discussing in one of the future videos, the scientists established that there was something missing in between Jupiter and Mars. And ironically, they actually discovered Ceres only a few years later, which was hypothetically that planet that they were missing. But then they started finding more and more asteroids, and it kind of put a dent into that theory. And they actually started realizing that maybe, just maybe, this asteroid belt that they started to discover was actually a result of a planet that was previously located in this area, but then something happened to it. And they actually back then proposed 4 major theories. One of them was that, well, maybe, just maybe, this planet was actually somehow destroyed by a collision with something else. In other words, possibly a very large object such as another planet may have collided with Phaeton and basically destroyed it completely, creating a lot of debris. So this was one of the propositions. The other one was in regards to this particular planet moving too close to Jupiter and basically getting shredded apart by Jupiter's gravitation. There was also another theory that proposed the hypothetical brown dwarf called Nemesis that may have actually destroyed this particular object. And last but not least was another theory that proposed that maybe there was some sort of a cataclysm on the inside of the planet, and it basically resulted in the explosion of this planet, which also resulted in the asteroid belt. Now, all of these theories were very interesting, and they tried to explain kind of something that we believed back then. We believed that this is the region where we should expect a planet, and because there was no planet but instead a lot of debris, we thought that it just something was there before, and that something was destroyed by some kind of an event. And it sounds like a pretty sound theory. As a matter of fact, it does have a name. This currently is known as the disruption theory, but most of the astrophysicists and most of the scientists today don't actually believe this is really what happened. As a matter of fact, there's really no reason for us to believe that this is what happened. And today, most scientists actually believe that it was actually the opposite, that it's not that something was destroyed, it's just the asteroid belt represents something that was never created. In other words, all of these rocks that you are about to see here, that are, I guess, are not as visible because they're a little bit dark, but they're also, there's like a lot of them here, they're also here along with the explosion I just created. These rocks are basically the result of something that was never really made. They represent the planet that was never born. So technically, the scientists back then were kind of right. Maybe there was supposed to be a planet here, but because of the Jupiter's gravitation and because of the all of the other stuff that was going on in the earlier solar system, this never became a planet. It just stayed as a shredded protoplanets and basically large asteroids that are there today. But nevertheless, that obviously doesn't change the fact that there are still people today that believe that Phaeton may have existed, and also some people believe that it still is somewhere out there, because that's kind of how we like to believe things. We love to think that something mysterious is just somewhere out there. And by the way, the word Phaeton is actually from Greek mythology as well. And it represents the son of Zeus, who actually, I believe he actually took Zeus's chariot and went for a ride, and then something happened and he crashed the chariot. And that's kind of how they decided to represent this object as well, because they thought it was something that crashed into Jupiter, into Zeus. Because in the story, I believe Zeus actually ended up destroying his own son. He basically got so mad at him for stealing his chariot that he completely turned them into pieces, just like Phaeton did in the story that we believed back then. But I guess what is important to take away from all of this is that we actually believed in this particular disruption theory for a very, very long time. We actually thought that this was true for at least 100 years, and some people even believed that this was true up to about mid 20th century, which is basically 150 years. And this suggests to us that there's some things today that we might think are true about our own solar system, or even galaxies and the universe in general. But with time, we might be able to discover new facts that will tell us that this is not true. So today we know that, almost for a fact, Phaeton was not a thing. And I just completely destroyed it by clicking on it. It was very likely never a thing. We're almost certain that this is just a region that never developed into a planet. So these are protoplanetary bodies, of which our own Earth is made as well. But there are definitely some other theories out there about our galaxy and about our solar system that one day will also be disproved, just like the idea of Phaeton. What they are, we obviously don't know just yet, but maybe it will be actually you disproving them in the future. Hello wonderful person, this is Anton and welcome to the system of Jupiter. In today's video we're going to be talking about the July 2018 discovery of 12 new moons around Jupiter that now put the number of total moons here to 79. So first of all, Jupiter already had a lot of moons to begin with. As a matter of fact, Jupiter currently stands as the record holder for the number of moons in the system. These moons can actually be divided into basically different types of moons. And as you can see, they all have very different orbits. But for the most part, you have the so-called classical moons or so-called Jovian moons, which are really just 4 moons: Io, Europa, Ganymede, and Callisto. You can kind of see them right in the center, and they all have relatively circular orbits with very, very specific patterns as well. There's also so-called regular moons. These are moons that are normally orbiting in the same direction as Jupiter and also have either relatively circular or low inclined orbits. So like, for example, there's a lot of regular orbits regular moons you can see in the middle here, such as Metis, Thebe, and so on. There's also irregular moons, which is pretty much everything else. This is one of such moons that has no actual name yet. This is another one, and what makes them irregular is basically that they have sort of their own orbit, and that's mostly because they were more likely captured asteroids or captured objects from Asteroid Belt or basically from outside of the solar system. These moons, however, the regular moons and the classical moons, were most likely made when Jupiter was being created as well. So what have we discovered? Well, we actually discovered 12 objects, and 11 of these are referred to as normal moons. Well, let me just kind of demonstrate to you by placing them in random orbits around Jupiter. And this is going to be at a distance where each orbit will take approximately 2 years. So we have, this is all randomly generated for now, but basically here are some of them. We're just going to place them right here. And here's a visual representation of these moons. I actually had to give them the direction opposite of the spin of Jupiter because that's kind of how they move. This is sort of yet another type of moons around Jupiter that have basically orbit in a direction opposite of everything else in the inner region of Jupiter. Now, we've discovered these moons while basically looking for Planet 9. In other words, the scientists trying to find Planet 9 accidentally discovered these 12 moons. But that's not all of them. 2 of them were a little bit closer to Jupiter, and they're actually all quite small, only a few kilometers in diameter. But 2 of them actually had orbits very similar to other moons of Jupiter. So in other words, these are actually regular moons of Jupiter. But then one of them was very, very strange. They actually refer to it as an oddball. And this oddball even has a name now. They gave it a name of Valetudo, which I believe is a Roman god of hygiene. Now I'm going to show you how Valetudo orbits. So remember, these moons are orbiting in clockwise direction. But Valetudo, which I just placed right here, has an orbit of about 1.5 years around Jupiter, and it actually orbits against the flow. pretty much every other moon is going this way, but it's going with the flow. It's actually going in the same direction as everything else in the inner system of Jupiter. And this is really unusual. Also, its size is about 1 kilometer in diameter, making this probably the smallest moon of Jupiter. Also, it really shouldn't be that circular. I think it's circular because I accidentally generated a circular object here. It's most likely more asteroid shaped. Now, this unusual moon has a lot of questions to answer. For example, why is it that it's actually on such an unusual path compared to other moons? And what actually created this moon? Its inclination is relatively similar to other objects in the inner Jupiter system, meaning that it most likely was formed when the planet was formed as well. So this is probably a very ancient moon, yet it's moving all by itself, really tiny piece against the flow. So some suggestions indicate that maybe this was actually a result of a collision early on in the Jupiter system, where it basically generated this fragment, and then it kind of flew to the outskirts of the Jupiter system, and now it orbits here for the rest of its time. But this suggests that maybe there are other objects similar to it that we will discover in the future. If this was a result of a collision, what exactly collided? And if it's not a result of a collision, so how could it possibly form otherwise? The other thing about this moon that makes it very unusual is that it actually has an extremely high chance of one day face-on colliding with other moons. And I'm going to demonstrate this in a few seconds by basically trying to collide this with another object going in the opposite direction. But it might actually take up to 1 billion years for it to actually have any serious risk, because these objects are really small and the distances between them are really large. Well, that's kind of all we know about this moon for now, and if you want to learn more about this or want to follow the actual study itself, this is from the Carnegie University, and I believe the principal investigator for this is Scott Shepard. He actually started studying or trying to find Planet 9 back in 2017, and since then this is actually what they've discovered: accidental moons. Well, let's finish this video by simulating what a collision with another moon would look like here. So we're going to actually pretend as if this is actually another moon going in the opposite direction and literally smacking into the object. The other object is going to be approaching Valitudo in a few seconds. I actually made a spelling mistake here. It's Valitudo, not Valitudo. And it's slightly larger. It's maybe about 1.4 kilometers or 1.6 kilometers in diameter. And they're moving toward each other at a speed of about 3 kilometers per second, because that's the orbital speed of these objects at this distance from Jupiter. This collision is most likely going to generate quite a lot of debris, and it's very likely that this will also result in some sort of a ring, specifically a ring around Jupiter at a relatively far away distance. So there's a high chance that if this collision ever occurs, Jupiter might actually get another ring. It already has a bunch, but it can always use more. So this is slightly slower than normal speed. It's about half the normal speed. But here comes the collision, and because it's head-on, it's going to generate a tremendous amount of energy, as you can see. So these large particles escaping from this collision might actually even end up on planet Earth. And that's about it. Now, interestingly, this basically almost completely stopped this object now. So it actually is going to start falling into Jupiter. And at some point, it might also end up re-entering Jupiter's atmosphere and basically falling onto Jupiter as well. And so here is Jupiter in all of its glory with all of its 67 known moons. This is the most massive planet in our solar system. It is ridiculously massive. It contains about 318 masses of Earth. And if we were to combine all of the other planets together, this planet here would still be about 2.5 times more massive. Essentially, it's very big and extremely powerful in terms of having influence in our solar system. But there's a lot of things we've discovered about this planet, because in the last 30 or so years, At least 7 different spacecraft visited it, this beautiful object, starting of course with the Pioneer 10, Pioneer 11 missions back in 1979. Then there was Voyager 1 and Voyager 2, which we actually do have in the game here under the objects, I believe. There is both Voyager 1 and Voyager 2, and you can actually even see them here in a kind of a historical way by typing Voyager, and here is actually Voyager 2 mission as it approaches Jupiter. So both Voyager 1 and Voyager 2 use Jupiter for the slingshot maneuver, as the other spacecraft did as well, to basically accelerate by passing behind it. So this is a very infamous maneuver that often used in astronomy, in space, to basically get a little bit of a boost, a little bit of extra speed. And so this happened in 1979 as well. Then there was a Ulysses craft in 1992, I believe. Then there was Galileo, Cassini, and the last one was New Horizons that then went to Pluto. And the 8th craft that is still around Jupiter today is Juno. The Juno mission is still active as of 2017 and is going to be exploring this beautiful planet for quite a while. And so what we've discovered with Juno mission and with the other observations is that, well, first of all, we've finally realized that, unlike previously speculated, Jupiter doesn't actually have any hard core on the inside. And when I say there's no core, I mean that there's no any kind of a hard planetary-like body on the inside below all of these, below all of this atmosphere. It was believed that there was something, but we've discovered that instead it has a very kind of a fuzzy mixture of layers of metallic hydrogen inside, and basically the interior of Jupiter is very irregular. There's no sphere on the inside that we thought there was. There's no any kind of a iron core, or at least Earth-like iron core that we thought would be there. And based on gravity measurements from Juno, we've realized that it's very likely that it's just basically entirely composed of this fuzzy-like irregular hydrogen and helium. And that was one of the more unusual discoveries and one of the more unusual confirmations of the last few years. We also know that it has the highest rotational velocity of all planets in our solar system. It rotates at about 12.6 kilometers per second, or 45,000 kilometers per hour, and it only takes about 10 hours to basically complete one rotation. And because of this, it's sort of shaped like a plate in a sense. So this way, it's a lot smaller than this way. And as a matter of fact, its equatorial radius is about 4,600 kilometers further away from the center. So it's sort of flattened because of the rotation. We also have discovered that the clouds on Jupiter are only about 50 kilometers thick. So this is a very thin layer. The rest of the atmosphere below the clouds is essentially pure hydrogen and helium. And the clouds are usually composed of ammonia crystals that are broken into 2 different decks that form different colors. So the darker material, the brownish material, is brought up from deeper inside Jupiter, and then it changes color when the sunlight acts on it. And so below these clouds, there is essentially the rest of the helium and hydrogen, but above the clouds is various types of ammonia crystals. Now, this right here is known as the Great Red Spot, and the Great Red Spot is actually something that has been shrinking in the last few hundred years. When we first discovered Jupiter, the red spot was several times bigger. Now it's a lot smaller, and we still don't really know why. But the interesting thing is that we actually discovered another spot somewhere on one of the poles right here, and this is known as the Great Cold Spot, and it's about the same size as the red spot. The cold spot is kind of hard to see. It's only visible using infrared telescopes, but it is there, and it's definitely, it definitely acts in the same way that the Great Red Spot does as well. And so that's something that's actually very unusual and very interesting. So basically, there's at least one more spot which suggests that maybe other gas giants like Saturn, Neptune, and Uranus may also have these tremendously large storms similar to a great red spot that are only visible in infrared and are somewhere in other parts of the planet. Now, the important discovery of Juno was in regards to the magnetosphere of Jupiter. So currently, if I actually enable the magnetosphere, you'll see that it's a tremendously large magnetic field. It's actually the largest magnetic field in our solar system after, of course, the Sun. And up to now, we believe that this particular magnetic field was about 5 Gauss in power, in strength. It turns out that it's actually a lot larger. It turns out that it's actually almost double of that, at least 9 Gauss. And the actual strength of the magnetic field suggests that whatever is creating it inside Jupiter must be able to create these super powerful magnetic fields, much more powerful than anything we have on Earth. Because on Earth, this is about 0.25 or 0.3-ish. Maybe maximum 0.65. So in other words, the magnetic field of Jupiter is like 50 times stronger than the magnetic field on Earth, which is very interesting, and also gives us an idea that maybe we can create or find a way to create artificial magnetic fields using the same idea, same technology, or same principles that the magnetic field is created on Jupiter. And this actually is very interesting because we also discovered that this magnetic field is not created the same way as it is on Earth. It doesn't come from within the planet. It appears that Jupiter's magnetic field is actually created on the surface. And we don't really understand how it's created just yet, but we know that the magnetic field seems to be mostly made by the surface of Jupiter, not by the inside. Once we discover how it's created, we might be able to somehow use this technology to create the magnetic field on planets like Mars, for example, that definitely needs a magnetic field if we ever decide to colonize it, because the atmosphere on Mars will not survive without a strong magnetic field. And this is Mars orbiting around Jupiter. And, well, apart from all of this, we also discovered quite a lot of other interesting things about the surface of Jupiter, specifically that it has lots and lots of various ammonia cyclones, ammonia storms. Storms that are basically raging all over the surface. Not just this one, not just the cold spot, but even smaller ones all over the surface of Jupiter. When I say smaller ones, though, I actually mean size of Earth about. So like this big. So they're Earth-sized cyclones, Earth-sized storms, pretty much at all times on the surface of this beautiful, massive planet. And more so on the equator side than the polar side. So the majority of storms actually occur right here. And, well, so far, these are the main findings from the more recent study about Jupiter. And hopefully this gives you an idea how incredibly mysterious this object still is. Even though we've known about it for like 400 years, more than 400 years actually, we've known about it since Galileo discovered it in his telescope. Even today, we don't really understand it very well. Some of the mysteries are actually very important for us. Like, for example, how does this planet create this unusually strong magnetic field around it? If it's on the surface, what causes this particular magnetic field to be formed? Is it something to do with the ammonia crystals, something to do with storms? Or is it something to do with the metallic hydrogen right underneath the surface? And other mysteries maybe are not as important, of course. Like, for example, the fact that obviously this planet has a lot of storms. It has so much atmospheric pressure and so much atmosphere on the surface that you would expect it to have storms everywhere. But on the other hand, understanding what's inside Jupiter and what causes it to be so interesting and so dramatic would definitely help us advance the knowledge of potentially terraforming, so that we can go on Mars, which is orbiting around Jupiter and causing it to actually heat up because of the various tidal effects, and then maybe somehow terraform it. But maybe all of this will happen sometime in the future, definitely not in the next few years. Hello wonderful person, this is Anton, and today we're talking about Jupiter, and specifically about what if Jupiter actually didn't exist in our solar system. What would really happen to the entire solar system, and would there be life on Earth? So Jupiter is the most massive planet in our solar system and has quite a lot of gravitational influence on objects nearby. But we know that Jupiter wasn't always located in this region of space. As a matter of fact, it's very likely that it was a lot closer to the Sun before. Now, this topic is actually based on a paper published by two scientists. One of them was Greg Laughlin from University of California, Santa Cruz, and the other one was Konstantin Batygin from Caltech. And what they decided to study is they looked at all of the other solar systems out there, specifically exoplanets in those solar systems, and they compiled a statistical representative of pretty much the average of various planets in those systems. And this is kind of what it looks like. So if I were to actually go to a different exoplanet, like for example, if I were to pick Kepler 11, you would see that things here are a lot closer to the star than they are in our own solar system. And as a matter of fact, the farthest planet is at a distance of something like under 1 astronomical unit. So like almost half, or maybe like 0.7 astronomical unit. And the closest planets are way, way closer. And so many of these planets are actually super hot, and this seems to be a pattern that's repetitive across the galaxy. Many exoplanets, many stars with exoplanets, seem to have planets that orbit very close, and also a lot of these planets are what we would call super Earths. They're basically 5, 6, 7, 8 times more massive than our own Earth. And on top of that, there doesn't really seem to be many other Earth-like planets. There might be 1 or 2, but not 4 like in our own solar system. So this created a bit of a conundrum. How is it that a lot of these stars have these super Earths, like Kepler 11e, at mass of 11 masses of Earth? And a lot of these are also ridiculously hot because they're so close to the sun, to the star. Here the temperature is 330 degrees Celsius. But on our own, or in our own solar system, on our planet Earth, things are a little bit different. So if we look at our own solar system, the majority of planets are relatively far away from the sun, and we have gas giants on the outskirts, and basically nothing like super Earths anywhere in sight. And so they decided to study this phenomenon and realized that, well, it seems that Jupiter might actually have a tremendous amount of influence. Furthermore, Jupiter is actually the reason why there are no super Earths in our solar system, because it very likely approached the sun relatively close, and we're going to just do that right now. We're going to remove the terrestrial planets, and we're going to add a bunch of super Earths, like Gliese 876d right here. So we're going to add a bunch of them orbiting around the sun, and we're going to move Jupiter to where they think it was, specifically at a distance where Mars really was. So something like 1.5 astronomical units. And the reason why it moved so close is because back then the sun still had a lot of dust around it, specifically stellar dust. And this dust, as it sort of collided with Jupiter, as basically Jupiter passed through these gas clouds. So we can emulate this by colliding a bunch of asteroids with it. So as it passed through this gas cloud, it got slowed down, and over time, this is billions and billions of years ago, it slowed down to be much closer to the sun. And because this was the first gas giant to be formed, it had quite a lot of influence. So we're going to move Jupiter a lot closer now, and here the distance is going to be about 1.5 astronomical units. And let's see what actually happens to those super Earths that are orbiting around our sun right now. We're actually going to remove some of the extra particles so that the game doesn't slow down. And let's run this a little bit faster and find out what actually happens. So because Jupiter is so massive and has so much gravity, almost right away it's going to start affecting these planets. And won't really take that long for them to start either flying away, or possibly colliding with each other, or possibly colliding with the sun. And according to the scientists behind this paper, a lot of them actually got projected into each other, and essentially they did this. So we're going to simulate this with this planet right here. They basically collided with each other, and here's that collision between two very large super Earths, and their collision created a bunch of planetesimals and a bunch of smaller objects, specifically similar to components that would then create Mercury, Earth, Venus, and Mars. So these collisions were the result of Jupiter causing quite a lot of trouble in this region. So let's just wait a little bit longer and see what actually happens to the system after just a few game years. So we're going to accelerate time once again, and we're going to run this simulation in relation to Jupiter and see what happens. And only within a few years, you'll notice that it already kicked out one of the exoplanets, or one of the super Earths, that is, and it changed a few orbits, not dramatically, but with time, with millions of years of this type of action, it would very likely change them completely. And so a lot of these planets would very likely end up colliding and possibly escaping the solar system, and possibly colliding with either Jupiter or each other. So Jupiter's action here was quite prevalent. Now, what happened after that? So there was a lot of basically mass here, a lot of planetesimals flying around, creating what would then become Mars, Earth, Venus, and Mercury. But then something else happened, and that was, of course, the creation of Saturn. And as soon as Saturn was made, it was also made a little bit closer, and it started pushing, or pulling, that is, on Jupiter. And this pulling action caused Jupiter to move away. It caused it to basically start moving out to where it is today, and over the next few million years, it's going to increase its semi-major axis to about 5-ish astronomical units. So all of this was basically because of the other second most massive gas giant, Saturn. And this scientific model actually has a name, and this name is Grand TAC. In this scenario, basically Jupiter kind of is perturbed by the gas first, comes closer to the sun, and then Saturn appears and moves it away from the sun. And a lot of things in the solar system change dramatically. And so because of this, these two scientists think that this is why we don't really have any super Earths. This is why solar system is so unique compared to other outside of solar system systems, specifically systems with the exoplanets. And this is also why it very likely caused a lot of collisions from the asteroids as it was basically moving around the solar system. And those asteroids in the early solar system brought quite a lot of materials to our own Earth. So things that we now take for granted, specifically things like water and organics, a lot of these things actually came from the collisions with various asteroids. And it's very likely that it was Jupiter that kind of brought them there through its gravitational interaction. Now, if Jupiter wasn't really there, we would still have quite a lot of super Earths, and it's very likely that our own planet Earth would look nothing like this and may have actually not even had any life on it because it would have been too hot. And for this reason, we have to kind of be thankful to Jupiter for its action. And even today, what Jupiter does for Earth is actually protects it. It protects it from things like comets and things like asteroids in the asteroid belt by pulling things away from here toward it and making sure that Earth doesn't get them. And also when comets come through the inner solar system, Jupiter often dislodges their path and they often collide with Jupiter, just like it happened in 1994 when we observed the collision between Shoemaker Levi comet and Jupiter. So this is what it is. This could have been landing on Earth and destroying life, but instead it landed on Jupiter. So this is why Jupiter is actually very important planet in our solar system, and this is how it may have actually created the life and caused our Earth to be the way it is. So if it wasn't for Jupiter, we probably wouldn't even exist. So the Universe Sandbox actually has a simulation called Exploding Jupiter, and here, as you can imagine, the only thing that does happen is Jupiter explodes. Let's observe this beautiful event from the moon of Jupiter known as Ganymede. And here, if you stay here long enough, you'll discover that things don't really go very well for Ganymede. As soon as the planet Jupiter explodes, after only maybe a few hours, things around Jupiter start kind of being destroyed as well. So you can kind of see the closer moons feel the heat first, and then the outer moons as well. And this is because what's happening here right now is all the debris is flying out at really high velocity and is colliding with the essentially surface of these moons. Now, what would happen if this beautiful planet exploded, but from the perspective of our own planet Earth? In other words, would anything happen to our beautiful planet if this kind of an event occurred? And today we're going to be talking about this event occurring in general. Do planets actually explode? Can planets actually explode? Have we ever seen a planet explode? If you want a short answer, the answer to all three questions is no. But let's talk a little bit more in detail about it. So let's go to simulation cold solar system. We're going to start right here. We're going to slow down things a little bit. And the thing is, if you just explode Jupiter right now, where is it? If you explode it right now, things just kind of disappear and done. So nothing eventful really occurs, because the way that the game processes things is basically to save memory, fragments disappear pretty quickly. But we're going to cheat a little bit. We're going to do the same thing, but this time we're going to tell the game to actually keep the fragments from Jupiter when it explodes. So we're going to initiate the explosion, and let's slow down time a little bit because it's going to happen pretty quick. And then as soon as this happens, we're going to select all of these fragments and do something really crazy. We're going to basically convert them into full body objects. In other words, they're going to become objects that don't just disappear suddenly. And here's what you're going to see happen in a few seconds. As soon as this occurs, if I actually zoom out of here, you'll see that a lot of these fragments that I have now converted will start flying apart and flying away from the central point where the explosion occurred. And they're going to start spreading across our solar system. It's actually going to look pretty amazing. So here, this is the explosion. This is really, literally what happens when a planet explodes. And if you look at each individual fragment, it's relatively big. It's sort of, I guess it's the size of a moon, a random moon in our solar system. Maybe even like a big moon, like kind of like closer to our own moon actually. So if I look at an individual fragment here, the mass of each of them is about 24% of our own moon. And they move at a speed of about 21 kilometers per second away from the central point. And what's interesting about this particular phenomenon is that this would require a tremendous amount of energy. And for this reason, because it requires so much energy, it's sort of kind of impossible for it to occur in real life, because planets don't really have anything that can make them explode so much. Unlike, sci-fi movies tell us, planets don't really explode, even if you shoot things at them with like super powerful weapons. I believe Scott Manley actually made a video about this once, calculating how much energy it would take to explode a planet if you had like a super powerful laser gun. And I believe this was sort of to commemorate the Star Wars release last year or 2 years ago. And he calculated that it would be just a ridiculous amount of energy that we just can't get out of a single planet or out of a single spaceship. And so this event is more or less science fiction. As a matter of fact, more fiction than science. But what's interesting about this is that it does look absolutely incredible. And I wanted to actually see if any of these fragments collide and affect our own planet Earth. So we're going to wait a little bit. We're going to wait for them to get to the part where our planet Earth is. But what do you think? Do you think they'll actually collide? Do you think anything will affect our planet Earth? I think that, because I know a little bit of statistics, it's very unlikely to occur. I don't think any of these rocks will actually make it to our planet or even come close to it. But let's see if I am proven wrong this time. So we're gonna wait for this, and I really just wanted to see how beautiful it gets as it spreads across from our solar system, because if I were to accelerate time here a little bit more, you would see that each of these fragments is actually just kind of escaping into the abyss of space, away from the central point where Jupiter used to be. And what's even more interesting is that, statistically speaking, none of these fragments will hit anything on the way, not even a single asteroid. At least it's very, very unlikely. And that's because there's just not enough fragments here. I mean, maybe in reality, if something did explode this way, there would be a lot more fragments. But with the amount of fragments that we created, which is probably in, I don't know, maybe like 1,000 or a couple of thousand here, it's not very likely that any of these will hit anything. So we can actually just look at Earth and see if any of them hit something. And just for fun, near the end of this video, we're going to take one of these fragments and actually collide it with our planet Earth. And oh wow, I actually found a fragment that was 10 masses of Earth. That is a little bit bigger than I expected. I think for the most part, most of them are about 24% of the moon. Oh, I guess some of them are a little bit smaller and some of them are way, way bigger. But notice how as they move away from the center, the distance between them grows more and more. And so eventually they'll kind of just all fly apart, leaving nothing behind. Now there's actually, there's a few articles you can find online about exploding planets. And the only scenario that scientists think may occur is if a large planet collides with another large planet head on. So in that case, there might be something that could resemble an explosion. But for a planet to actually explode, and we're going to do this maybe with just another, let's just do it with our planet Earth. Let's come closer to it. And I'll just show you the energy required here. Let's slow this down for a second. If you go into the explosion, it actually shows you how much energy you need to explode this object. And here you can even change it to, let's say, the megaton of TNT. And if you look at it, it's basically equivalent to having like a 2 or possibly even 3 kilometer in diameter of a ball of uranium. So if you could find so much uranium and put it in the middle of that planet and then explode it from there, maybe it would create this much energy. But even then, there's just way too much stuff on the inside of our planet that would probably stop the nuclear reaction from spreading. So even with that amount of uranium, it's very unlikely that anything would explode a planet. Now, it looks like these fragments actually kind of flew apart too far. You can still see them right there. So this kind of is not as fun as it used to be. Let's see what would happen if one of these fragments actually did collide with our planet. So we're going to slow down this maybe a little bit more. And we're going to take, select one of these fragments wherever they are. And using the same mass, we're going to collide it at the same speed of 18.3 kilometers per second with our beautiful planet Earth. So let's see what would happen. And here's actually what one of these fragments looks like in comparison to our own planet Earth. Here's what it is from a distance if you zoom out. And let's actually discover what would actually happen if one of them did strike our planet. You can imagine nothing good. So the chance for this happening though is pretty low because Jupiter is separated into these very large chunks that seem to be a little bit too big for them to collide any specific location in our solar system. So this does look very beautiful, but even though this looks like a huge explosion, this is only on the surface. The inside of the planet are just fine. They're still quite stable and would only be affected if something really just went through our planet Earth. But even then it would not really explode. So for a planet to explode scientifically, there is just seems to be no mechanism we're aware of currently that would make it happen. So don't expect any planets to explode anytime soon, or really ever. Stars, on the other hand, do it all the time, and nova and supernova are very regular occurrences. And so there you have it. So we basically simulated the explosion of Jupiter, the collision with our planet Earth of one of those fragments. And I guess now what we can do is maybe see what would really happen if, I guess, Jupiter exploded next to our sun. There's another simulation called Sun and Exploding Jupiter. Now let's see what happens here. And as you can see, as soon as the Jupiter planet explodes, all of its fragments just kind of sort of get absorbed into our own sun. Now, this actually probably did happen. The planet might have not exploded, but sun that we currently have seems to have a relatively high metallic content, meaning that our own sun probably swallowed quite a few fragments that may have become planets or may have even been planets. So swallowing a Jupiter or two may have been actually part of our sun's diet. So you may know a little bit about Jupiter and its 67 confirmed moons. All of them are actually visible right here, especially if I enable the orbits or the trails. Now, a lot of these moons are very, very small. They actually used to be asteroids that got captured by Jupiter over the billions of years of its existence. But 4 of them are very large. Callisto, Ganymede. Ganymede is actually the largest moon in our solar system. Europa and Io are pretty big. There, as a matter of fact, not too far off from some of the planets. Ganymede, as a matter of fact, is larger in terms of size than even the smallest planet, Mercury. You can actually fit Mercury inside. So I thought, well, why don't we try to place all of these planets that we have, specifically 7 of them, around Jupiter and see if we can actually create a customizable or customized Jupiter system. Is it possible? Well, let's find out. We're gonna do this in descending order first by placing Jupiter in the middle, then using the binary system with balanced motion to place Saturn somewhere not too far off from it, because Saturn is actually relatively similar to Jupiter in mass and in size, just a little bit less massive. Saturn is about 100 masses of Earth, whereas Jupiter is about 3 times as heavy. So here, both of these planets will need to be kind of balancing each other's motion and orbiting around one another. Almost creating like a dual planet system, actually. Now let's place some of the other objects. So let's go with the next heaviest object, most massive object, and that's Neptune. We're going to place Neptune a little bit farther away. Then we have Uranus. And then we just wait, because it already seems like it's not going to work. Look at that. Yep. Neptune got destroyed completely within seconds. So that didn't work. Alright, let's try this a little bit differently. Let's place Jupiter in the middle again. And this time we're just going to use normal orbits and place Saturn around it. Then Neptune will be next, a little bit farther away. And then Uranus. Let's see if this actually works. So we're going to wait right here. Wait a few in-game weeks and see if this works. And as you can see, both of these planets already kind of acquired a very interesting orbit around one another, with Neptune once again getting attracted too close and very likely being destroyed any second now. Unless I magically created a stable system, and I totally didn't. It is now part of Jupiter. And Uranus might be next, because this is definitely not a stable system either. So far, we kind of failed. So far, it's actually a lot more difficult than you can imagine. Alright, well, let's try this again. Attempt number 3. Let's try this a little bit differently. Let's place Jupiter first. And now start with the smallest planet, Mercury. We're actually going to create a miniature solar system. We're going to place Mercury here. Zoom out a little bit, place Venus. Zoom out a little bit, place Earth. And now place Mars. Let's run this to see if this is stable. And you can see Jupiter lighting up, and that's because there's actually a bug in the game where the tidal forces seem to affect the planet that objects are orbiting around, not the other way around. So there's a slight bug. That's why Jupiter is suddenly so hot, because of the tidal effects that it really shouldn't be getting. But as you can see, this looks pretty stable, right? We were able to place 4 satellites, which used to be planets, around Jupiter. Okay. Can we place one more? Let's go with the next most massive object, Uranus. We're going to place Uranus a little bit farther away. Maybe a little bit, yeah, right around here. And wait a little bit as well. Actually, we can probably place Neptune as well. And if things go wrong, they go wrong. Let's place Neptune, and now let's wait again. So we currently have 6 satellites. 6 planets orbiting around Jupiter, with only 1 missing, Saturn. And that's probably going to be the most difficult to place. As you can see, the system still seems to be kind of stable, even though Jupiter started moving around because of the attraction from Neptune and Uranus. But nevertheless, this seems to be, at least for now, a stable planetary system with basically 6 moons that are actually really, really massive. Which kind of makes you think, maybe somewhere out there is actually a planet or an exoplanet that does have something very similar. It might be very massive itself, and it might have really, really massive objects like Neptune,
which normally would be known as super Earths. This is a type of a planet that is known as a super Earth, basically orbiting around that planet. So what do we do with Saturn? We have to place Saturn very gently somewhere so it doesn't destroy this beautiful system for us. We're going to maybe place it in the opposite direction of the motion of Jupiter at a slightly higher distance, so maybe around here. All right, let's try this and see what happens. Maybe a little bit farther. Boom. There is a Saturn. And let's see if this actually worked. It's for some reason actually under an incline. And just for fun, let's actually add the rings to Saturn as well, because, you know, Saturn does have rings. So we're going to slow down just a little bit and add a few rings of Saturn right there. Beautiful. So now Saturn has realistic rings that are orbiting around it as it basically orbits those planets in a distance. Or actually, it's technically orbiting Jupiter. Now, what do we have here? I don't see Mercury anymore. No, it's here. Mercury, Venus, Mars, and Earth. So the orbits shifted a little bit. Uranus and Neptune are still there as well. And Jupiter is going to start moving towards Saturn probably. But let's see what actually happens. We're going to wait a few years, in-game years, and find out if I was able to create a stable system with everything as a moon of Jupiter. It's very likely that it's still not very stable because I can see some of these planets share in the orbit. But for all we know, we might have actually done it. We might have actually created a stable system. And you can kind of see the rings of Saturn spinning right there in the distance. It looks very, very beautiful. But so far, so good. So let's see how long the system survives for. Because it's still not very stable. There's no resonance between the planets, meaning that at some point they might crash into each other. There's also no resonance between the larger planets. So they're going to at some point start attracting the smaller planets and pushing on Jupiter in a way that is going to destabilize other orbits. But I still would like to see how long this lasts for. So far, we've definitely succeeded. But I have a feeling it's going to be destroyed soon. You can already see Mercury slowly losing its orbit and being kicked out of the inner Jupiter system into the outer Jupiter system, where it might actually become a moon of, what is this? Uranus. Or something else. Anyway, so let's accelerate this and just watch the magic happen at slightly faster pace. So you can see Jupiter is moving quite a lot. It's definitely being pushed and pulled, not pushed, but definitely pulled by various gravitational forces from Neptune, Uranus, and Saturn. And it's creating these beautiful shapes that I believe Vsauce very recently talked about. There's actually a name for the shape, and if you remember what it is, do post it in the description, or in the comments below, because I think everyone should know what this is called. And I'm not going to spoil it for you. Google it up, find out what it is. It's a very cool mathematical shape. And anyway, so looks like, I don't know what happened here, but our Saturn is very close to us, and its rings are going crazy. Its rings are actually out of control. We also kind of lost Mercury, I think. And Neptune just flew away as well, because Saturn decided to kick it out of the Jupiter system. I'm not sure if they're still in orbit. They might still actually be in orbit. We can check that by clicking the orbit here. And it looks like Mercury is definitely not. Mercury has definitely departed and flew away. So this is officially the end of that stable system that we created. It lasted for about 2 years. You can see that this is a size comparison of these planets. I clicked the chart accidentally, but it's a pretty good way of seeing the size comparison between the planets. But basically, there you go. So creating a stable system with Jupiter, where all of the moons are basically other planets, is very challenging for as long as Saturn is involved, because Saturn will definitely disturb the system. If it wasn't for Saturn, we probably could create something with Uranus and Neptune, because they're not massive enough to affect the system. But Saturn does have a lot of mass, and it's definitely going to create a lot of chaos. And, well, that's really all I wanted to say in this video. I wanted to see if we can do it, and we kind of did it for a little bit, but definitely not for a long time. Let's actually just compare the size once again, just so you can see how similar in size Saturn and Jupiter are. And Neptune and Uranus are significantly smaller, but they're relatively similar to each other. And then we have Earth, Venus, Mercury, and of course, a fragment that I think used to be... I think this used to be Mars. I think Mars actually got destroyed by something, and we totally missed it. Yeah, I can see that Mars actually very likely got destroyed by the tidal forces of Jupiter because it approached it too close. You can kind of see the leftover fragment orbiting here, and that's because it's very likely just disintegrated and became a bunch of not asteroids, but a bunch of rocks. I can kind of show you what I mean by this by using Venus here. We're going to actually decrease the semi-major axis of Venus, making it approach a little bit closer, just so you can see what actually happened to Mars as well. So let's cause the same thing to happen to Venus, and maybe not too close yet. And so here we go. Venus is also going to disintegrate into little pieces and become just a fragment any second now, especially if we increase its eccentricity. And there you go. So this is kind of what happened to Mars. Now, the reality is that this is actually how all of the rings of Jupiter, Saturn, Neptune, and Uranus were created as well. An object that was similar to an asteroid, or very likely an asteroid, approached too close to the gas giant, or to the ice giant in case of Uranus or Neptune, and it basically disintegrated, creating what you see right here as rings. So this is essentially how all of the rings were created in our solar system. Hello wonderful person, this is Anton, and this is Jupiter and Saturn. In today's video, I actually wanted to discuss a very interesting hypothesis/theory that focuses on the fact that both of these planets have different number of very, very large satellites. Jupiter seems to have a lot more. It has 4 large satellites known as Io, Ganymede, Callisto, and Europa, whereas Saturn only has 1 known as Titan. And there is actually a very interesting reason for this. In today's video, you're going to find out why, and hopefully you're going to learn something new. And so, as I mentioned, Saturn seems to only have 1 large satellite known as Titan, which is basically the second largest moon in our solar system, slightly larger than our own moon. If I were to place moon here, it would actually be a little bit smaller, and slightly smaller than Ganymede. So, there's only 1 of these though. Jupiter, on the other hand, has 4 of these large moons, and they're basically right here. There's Io, which is actually relatively large at about 1.2 sizes of or masses of our own moon. There's Europa. There is Ganymede, which is the largest satellite we have in our solar system, that is actually even bigger than Mercury. And finally, we have Callisto. So if we were to look at the chart here, there they are, these 4 very large satellites known as Galilean moons, much larger than the closest moon to them. Now, why is it that Jupiter has 4 and Saturn has 1? For the longest time, scientists thought, well, maybe it's actually because Jupiter is technically more massive than Saturn, and because it had a lot more mass when it was forming, and so it got to create more satellites. This is Saturn for comparison. It's about 3 times less massive than Jupiter. But the reality is actually a little bit more tricky than that, and the reality has to do with the actual formation of these planets early in the formation of the solar system. So when they were still part of the protoplanetary disk, which you can kind of see represented by these yellow particles everywhere here, both Jupiter and Saturn were basically part of their own protoplanetary system where there was actually a disk orbiting around them. So let's just actually take a look at Saturn. And so here is a kind of a protoplanetary disk, or I guess planetary disk, orbiting around Saturn, which will eventually result in formation of various moons. Now, both Saturn and Jupiter had these, but the thing about Jupiter is that since it's more massive, it was able to collect, or I guess suck up, a much larger protoplanetary disk, thus clearing a much larger area than did Saturn. So this is what the Jupiter's protoplanetary disk looks like. Or I guess in this case it would be called proto-moon or proto-satellite disk. And this is a slightly smaller disk of Saturn. And because Saturn is slightly less massive than Jupiter, it wasn't actually able to clear this area of protoplanetary disk around the Sun as quickly as Jupiter, and so it couldn't actually collect as much material as fast. Jupiter, however, cleared this area really fast and started to coalesce its satellites, and at some point it basically started to look very similar to how it looks today. So here I just placed 5 random moons orbiting around Jupiter, and these 5 moons were created from this proto-satellite disk and basically started to kind of slow down because of all this material flying around Jupiter. But because Jupiter is so massive, it was actually able to clear all of this stuff very quickly, and so these moons didn't really get to slow down as much. Maybe some of them actually disappeared and some of them crashed into Jupiter, but the majority of the big moons kind of just stayed in the same area. So because of the actual mass of Jupiter, this area was cleared very quickly, and all of this proto-satellite stuff kind of just disappeared. However, in case of Saturn, these large moons that were formed from all of this material ended up not really getting the same sort of treatment because a lot of this material didn't disappear as quickly. Saturn was not as, or is not as massive as Jupiter, and so proto-satellite ring stayed here much longer. And because of this ring, these moons actually started to slow down over time. So I'm going to simulate this by basically literally slowing down this moon and manually changing its velocity. Now let's actually just see what happens to it as we pretend to slow down as it passes through all of this material and through all of this stuff that's orbiting around Saturn. And there you go. It basically collided with Saturn. And so all of the large moons that were present around Saturn in the beginning ended up colliding with it, except for Titan. Titan was lucky enough to be far away and could actually wait long enough for all of the other moons to basically either disturb the proto-satellite disk or essentially collide with Saturn. And by the time Saturn finished forming its moons, and by the time the proto-satellite disk completely disappeared, which we're going to do right now by erasing all of these particles, Titan was already in a relatively stable orbit around Saturn, with all of the other smaller moons orbiting around it. Now, so this is essentially the very interesting explanation for why Saturn only has 1 large moon, whereas Jupiter has 4, Io, Ganymede, Europa, and Callisto, and this also explains why Ganymede also happens to be a little bit closer to Jupiter than other satellites, because it's more massive, it's actually larger, so it would have been affected by this proto-satellite disk a lot more than moons that are slightly less massive and are farther away. In other words, one of the reasons why Ganymede is so much closer to Jupiter than other moons is because it actually got affected by these tiny proto-satellite particles that used to exist here, and that basically slowed it down and made it approach Jupiter closer. And had it actually stayed around longer, in other words, if the proto-satellite disk was a little bit more massive or stayed around in the system longer, all of these moons would have actually also collided with Jupiter and would have actually completely disappeared, and it would have no large moons whatsoever, only smaller moons that it has today. And so just to summarize, the only reason that Jupiter has 4 large moons and Saturn only has 1 is because of the early proto-satellite disk that essentially slowed down all of these other moons and made them collide with its parent body. And so had Ganymede stayed around the proto-satellite disk a little bit longer, and had it actually decreased its speed even less, it would have actually very likely collided with Jupiter as well and combined with it. But as we have it, it just so happens that Jupiter was actually massive enough to get rid of this proto-satellite disk relatively early, and this actually saved its large Galilean moons from complete and utter destruction that you're about to see as I collide this beautiful and extremely large moon called Ganymede with the largest planet in our solar system, known as Jupiter. And there's actually the shadow of Ganymede approaching Jupiter, and here we go. Here comes the collision. So this is what would have happened had the proto-satellite disk remained.
Hello wonderful person, this is Anton, and in this video we're going to be talking about this beautiful creation that you see on the screen right now, Jupiter. Today we're going to be talking about very unusual amount of new discoveries that were coming out of NASA and specifically out of the Juno mission that suddenly all were explained to us in the summer of 2018. We're going to find out what these three unusual discoveries are, and today you're going to learn a little bit more about this beautiful planet. So for the longest time, we've had quite a lot of questions about Jupiter, and now that we have an actual active mission around it, we're able to answer some of these questions. But what's interesting is that a lot of the answers that we've been getting from the Juno mission are not actually to the questions we've been asking. So first of all, let's start with the first discovery that was basically explained and released just a few weeks ago in late August of 2018. Apparently, the magnetic field around Jupiter is totally out of whack. It's nothing like the one around Earth, it's nothing like the one we actually expected to see. And even though for the longest time we actually expected to see this, because you know that's what Earth kind of has, we instead saw this. Now, explaining this currently is kind of beyond our abilities. We actually have no idea what's going on here. We were even very surprised to find out that the poles, the magnetic poles, are totally in random positions. So like, for example, you see the positive side here is, I guess, a little bit off the North Pole, but then the negative side is actually on the equator. And then there's actually another one right there. So as a matter of fact, it has two negative poles. And it also seems to be very chaotic, very unpredictable, and seems to also change quite a lot as well. Now, this was the first discovery. We still don't really know why this is happening. We just realized that it does happen, and that because of this, the actual magnetic field around Jupiter has a very, very varied influence on its moons and also on the other objects that might actually come close enough to be influenced by the field itself. So that's the first discovery, but related to it, we also kind of are now able to explain why, if you were to actually come really, really close to the surface of Jupiter and to kind of actually look at some of these cloud formations, you would realize how weird they are. And they are actually so strange because of the magnetic field. And so if we were to actually take a look at these clouds in infrared and basically kind of look inside on what's happening beneath sort of the surface layer, we would see some incredible things that kind of resemble the surface of the sun. As a matter of fact, if you were to look at this and not know that this is actually infrared of Jupiter, you would totally think this is on our own sun. And we know that our sun has these because of the magnetic field. And it seems that the Jupiter's activity on the surface is also practically mimicking the same effects. It's absolutely and totally dependent on this unusual magnetic field that it has coming from the inside. And so these absolutely incredible images of Jupiter with this really crazy looking cloud cover can totally and absolutely be explained by the effects of the unusual magnetic field and specifically the interaction of various magnetic lines coming from inside Jupiter. So here, this is kind of reminiscent of what we might actually see on the surface of a star as well. And we know that stars get these spots only because of the magnetic effects and magnetic lines. And we know that stars get these patches and dots because of the magnetic lines and because of the magnetic field itself. And so that's the second unusual effect that was actually kind of unofficially explained. And the third discovery coming from Jupiter is coming to us straight from here, the great red spot of Jupiter. And what we've discovered is that inside of this beautiful spot, if you were to actually try to go underneath all of this surface layer and try to jump inside, what you would discover is a beautiful layer composed almost entirely of water molecules. And what's even crazier is that it's actually a lot of water. It is a tremendous amount of water. So in other words, we actually discovered a huge deposit of water inside the red spot, the Great Red Spot of Jupiter. And what's even crazier is that it's not just any kind of water. It's water at a pressure of about 5 atmospheres inside the actual cloud that gives it enough temperature, about 0 degrees Celsius, to actually become liquid droplets of water. So there's literally a cloud of water vapor that is sort of circulating around that Great Red Spot that could potentially also have, well, life? At least that's the official speculation coming off some of these scientists right now. If you have liquid water, you could potentially have life, and if there's actual liquid water droplets in that Great Red Spot, we could potentially find some kind of atmospheric life. Now, maybe, maybe not. We'll see when we get there. And in a nutshell, that's basically what we've discovered in the summer of 2018 about this beautiful planet known as Jupiter. We've discovered it has unusual, very weird magnetic field. We also discovered that this magnetic field creates these unusual clouds we see on the surface, and that somewhere out there, there's actually liquid water on the inside, potentially enough to actually be viable for life.
Hello wonderful person, this is Anton, and in today's video we're going to be talking about the Juno mission and our beautiful Jupiter. In 2017, Juno discovered some of the more incredible findings about this unusual planet and redefined our understanding of it. So even though Jupiter actually looks very, very incredible in Space Engine, we're probably going to be using another application known as NASA's EYES, where we actually get to see the Juno mission and find out exactly what it discovered around the beautiful Jupiter that doesn't look as beautiful in here, unfortunately. Now, first of all, this application is totally free, so you can download and check it out by yourself. But what I'm going to focus on are the 3 very unusual findings that totally blew the scientists away because they thought Jupiter was this, and turns out it's something completely different. Now, you can actually discover a lot of things about this mission by clicking these buttons right here. Like, for example, this shows you the orbital insertion that occurred back in 2016. And you can go through very specific mission parameters here. So, depending on the timeline, you can actually scroll through and just to see what happened. So, in short, it took about half an hour for the Juno mission to insert into Jupiter's orbit. But we're going to go into the science of Jupiter, and I want to talk about what we've discovered so far and why it's actually kind of groundbreaking. So here you can totally just change any of these parameters and look at what Juno discovered. Now, one of the goals of Juno mission is actually to study the atmosphere of Jupiter. And here we actually are going to be looking inside the atmosphere and try to find out what's going on inside of this beautiful gas giant. If you actually go on YouTube, you can find a video by NASA that shows you a really cool simulation of us flying through upper atmosphere and going inside the red spot of Jupiter. And here it shows you the altitude and also the temperature that's going to pop up here in a second as we fly into this beautiful, very, very scary looking cloud that's also a superstorm, the biggest storm in our solar system. So here the temperature goes up to about 500 degrees Kelvin, which is close to about 200-300 degrees Celsius. And this is inside the red giant spot of Jupiter. So we're basically studying the interior of the atmosphere, and here in NASA's EYES you can kind of sneak a peek at what's going on inside. Now, one of the more unusual discoveries is actually in regards to this right here. So the atmosphere hasn't really been studied very well yet, but we discovered that we thought that there was actually a solid core inside Jupiter, but it turns out that it's very likely not solid at all. It's very likely that it's some sort of a fuzzy, unusual super material that is kind of dissolved and dissolving everything, and is not something that we can easily imagine because it simply doesn't exist on Earth, because these conditions are really extreme. It's super, super hot here, up to about 10,000 degrees Kelvin, and it also has really ridiculously high pressure of over 2 million atmospheres. So in these conditions, this becomes a completely different material and a completely different type of environment that we just don't understand very well yet. But this was one of the more unusual discoveries, so forget about the solid core, it doesn't seem to exist. Instead, it's a fuzzy core. Material and environment that we just don't really understand very well yet. Okay, so this was the interior of Jupiter, but we also discovered some really cool things on the exterior, specifically at the polar poles here. Now, it's a little bit difficult to see it in this simulation, so I'm going to show you the photo instead. And this is actually what we saw at the northern and southern pole of Jupiter. These unusual, chaotic looking cyclones, very similar to hurricanes on Earth, obviously a lot larger in size, but also very chaotic, very random, and basically very unusual looking. As a matter of fact, just the fact that they are on the southern and northern pole is kind of weird to begin with, because on Earth, most of our cyclones happen in this area right here. We don't really get much in terms of cyclones or hurricanes or typhoons in the southern and northern pole, but Jupiter does, and it's very unusual that they're so random, so beautiful, and so crazy looking. So that was actually a very unusual discovery, something that we didn't expect at all. And obviously we have no idea how these are formed and what makes them so unique looking. Well, that's discovery number 2, and another redefinition of our understanding of this beautiful planet. And the third component that we were really surprised to discover and analyze is this, the aurora. Aurora of Jupiter are something that we thought we understood because we know that it's formed because of the magnetic field, magnetosphere, but turns out Jupiter's aurora are also very different. As a matter of fact, first of all, they're about 10 times stronger than we anticipated. We thought this particular aurora is about 10 times stronger than on Earth, but it turns out that it's like hundreds of times stronger. On top of this, unlike on Earth, these unusual phenomena actually act independently of each other. What this means is that, so if there is an aurora right here on the northern side of Jupiter, whenever the other side of Jupiter, in other words, the southern pole in this case, becomes sort of dark and is not facing the sun, this aurora disappears. So they actually are totally independent of each other, which is not something we understand very well, because on Earth, the aurora on one side of the planet will always result in the opposite side having them as well. But on Jupiter, it doesn't seem to happen. This can happen without this ever occurring, which means that the mechanism for aurora formation on Jupiter, and also the mechanism for making them so powerful, is totally beyond our understanding. We have no idea why, how, and what's happening here. So this is something that Juno mission is actually going to be studying, because we've already studied the radiation field right here. I'm actually going to remove the rings here. This is what the radiation field of Jupiter looks like. This is the radiation field formed by the magnetosphere. In our around our planet, this is also known as the Van Allen's belt. But here, the magnetic field is what we don't really get. We don't understand how the aurora and the magnetic field interact on this beautiful planet. And by the way, you can actually just remove all of this and take a look at just aurora, and there is the northern one, and there is the southern one, but like I said, they seem to be independent of one another. These are actually based on actual photos that Juno mission took. And what's really cool about this particular simulation, known as NASA's EYES, is that you can totally go and find out what apparatus is used for what discovery. So here we can take a look at microwave radiometers, and it kind of gives you the brief overview of what these actual tools are, what they do on Juno, and how they look in real life. This is actually something that the previous missions and previous apps didn't really have in NASA's EYES. And here I really like how they made it very explanatory, very clear at what's doing what and how it works and what's inside. Pretty cool addition to this already awesome free app. Anyway, back to Jupiter. So, for the most part, that's kind of all we've discovered so far that is revolutionary and mind-blowing, because we thought we understood gas giants kind of a little bit, but turns out we really don't know what's going on and how things are working there and what causes them to be so very strange, so powerful, and so unusual. Now, the purpose of this mission is, of course, to study the atmosphere, to study the magnetic field, and to also study the internal parts of Jupiter, which is what this mission is going to be all about in the next few years. And within the next few years, we'll hopefully learn a lot more about gas giants, understand them a lot better, which will obviously help us to not only prepare for a colonization of the moons of Jupiter, but also possibly colonizing the planet itself by building all kinds of really cool cloud cities like in Star Wars. And let's start with the #1 unknown mystery about this beautiful planet, and that's, of course, what is actually inside of it. Its composition. We know that its composition doesn't seem to meet the modeling of planetary creation because it seems to have a lot more stuff that is not hydrogen and helium. In other words, Jupiter's metallicity, a concept about which I've talked about in a previous video, doesn't seem to match the models. It has very high metallicity, it has a lot of stuff that is not hydrogen, not helium, and this suggests two things, or I guess at least one thing. And that's that Jupiter over time absorbed a lot of rocky materials and a lot of possible planetary bodies. It may have swallowed a lot of Earth-like planets or planetoids that would have created planets. And it seems to have all of this stuff inside now. So it seems that Jupiter has several Earth-like bodies on the inside, which is very unusual and very interesting. And mystery #2 is in relation to how this beautiful planet was actually made. Now, we don't really know specifically where it was made and how it was made, and we don't really know if during its creation it had a lot of effects on other planets. As a matter of fact, one of the previous videos I made was about a paper that suggested that Jupiter at some point kicked out another gas giant from our solar system, and that we used to have 5 gas giants, not 4. And this, all of this basically gives you an idea that we don't really know much about the creation of Jupiter, and we don't really know exactly how it formed. We have ideas, but none of them have actually been proven yet. But the two most prominent ideas right now basically tell us that this massive planet was either formed farther away from the sun, then migrated inward and changed a lot of orbits of other planets in its path, or it may have been actually formed where it is today, and then a lot of objects were sort of dragged toward it and it absorbed them as they came close. So maybe one day we'll find out, but definitely not today. Now right now we're flying through Jupiter's rings, which you may have known that Jupiter does have. So we do know that Jupiter does have rings like all of the other ice and gas giants in our solar system. But what you may have not known is that Jupiter also has a lot of water. As a matter of fact, this is the most massive water body in our solar system. It has more water than any other planet, any other object out there, at least in our solar system. Now, we don't really know where this water came from and how it ended up inside of this beautiful planet. But if we one day learn how the water came here, it may help us understand how water on Earth appeared as well, because we don't even know where our water came from. We thought it was from comets, but then we measured water in one of the comets and found out that the water there was completely different. So maybe it is not from comets at all. So we know that water is here and it came from somewhere, and we know that understanding where water came from will help us understand how life was formed on our planet, and of course how life might actually form on other planets out there in other solar systems. So figuring out where Jupiter got its water is kind of important. And interestingly, in 1994 there was actually a comet that collided with Jupiter by the name of Shoemaker Levi 9. This comet created a huge water cloud in the upper atmosphere of Jupiter, and you can still even detect that cloud there today. So water seems to not only arrive to Jupiter, but also seems to stick around for a very long time. So there's quite a lot of mysteries related to water in this particular planetary system. Now, mystery #4 is all about this beautiful giant red spot that is very, very familiar to us, because this is essentially how most people can tell Jupiter apart right away. Now, what is the mystery here? Well, there's actually quite a lot. For one, we don't really know how deep it goes and what's underneath of it. And two, is that we don't really know how it formed and why it's been shrinking. In 1930s at least, we know that the size of this thing was about 3 times bigger. Today, you can barely fit Earth inside. Back then, you could actually fit 3 Earths. So the size of this thing has changed dramatically. But why? We don't really know. And we don't even know what's powering it. Why has it lasted for like hundreds of years? What's happening here? What is this thing? And we know that other gas giants and ice giants have them. So what makes them the way they are? Okay, now let's talk a little bit more about the hydrogen inside this planet. 90% of mass here is essentially hydrogen. But as you go deeper and deeper into the planet, we think that this hydrogen loses its electrons and becomes metallic. It becomes very similar to metals on Earth and basically starts conducting electricity. We think that basically because of that, this planet has a very powerful magnetic field. As a matter of fact, it has the most powerful planetary magnetic field in our solar system. But what is going on with this hydrogen inside and how exactly it forms all of this, and essentially how this magnetic field is formed, is a huge mystery. We know, or we think we know, how magnetic field on Earth is formed, but how it is created in this particular planet is totally not really understood at all, and is all based on hypotheses and ideas that are not particularly proven yet. And the thing is, understanding how magnetic field is formed on Jupiter is very important because we need to have magnetic field to survive. And so if we're going to be exploring other planets, we need to be able to predict if they have magnetic fields. So how it's formed and whether other planets in other solar systems have magnetic field is very, very, very essential. So that's essentially mystery number 5. And mystery number 6 actually relates to magnetic field. And specifically, it relates to something I'm about to show you that's right here on one of the poles of Jupiter. Jupiter, like many other gas giants, has aurora. Aurora are these beautiful lights that you see that are formed right here, and I can maybe make them a little bit more visible if I change this light settings a little bit and possibly come a little bit closer as well. So we know that Earth has them, obviously, and this is because when some of the solar radiation comes to Earth, it interacts with the magnetic field of Earth and creates these beautiful visible lights. But on Jupiter, things are a little bit different. We know that Jupiter can actually create them without any solar interaction. How? Well, we're not entirely sure, but we think that it's somehow related to the volcanic eruptions on the moon of Jupiter known as Io. So when the volcanic eruptions occur on Io, they essentially create a lot of charged particles. And these charged particles then end up in the polar regions of Jupiter and create the beautiful aurora effect. But the problem is that we have no idea how they make it from all the way here down there. That's a huge mystery and still has not been explained. And so maybe one day we'll be able to answer this question, but for now we'll just have to accept the fact that Jupiter's aurora are very powerful, very beautiful, and are possibly created by Io's eruptions or possibly by some kind of a different mechanism that we still don't understand. And the last mystery of Jupiter is in regards to its surface, and specifically in regards to the following. If I come really close to Jupiter here, and if I actually look at it, you'll notice that it has these different bands on its surface, and all of these bands are colored differently, and they have slightly different composition, and potentially different things happening inside of them. But what's really interesting, and what's unfortunately is not shown here, but you can kind of maybe see here, is that they're moving at different speeds. All of them have different velocities, all of them have different rotation speeds, and we don't really know why and what makes them slow down in certain regions of Jupiter and what makes them accelerate in other regions. And they also seem to have different speeds depending on whether it's sunlight or night. So there's a lot of mysteries in regards to these bands, how they're formed, and what makes them spin and rotate at these particular velocities. And so that's essentially all I wanted to talk about in this video. and I wanted to mention these 7 unusual mysteries that we still cannot explain about Jupiter. Even though we've known about this planet for hundreds of years and we've explored it using several probes, we don't know enough about it, and there's still quite a lot of mysteries that hopefully one day we'll be able to solve, because they will help us understand how other planets work, how the life on our Earth was formed, and potentially give us new theories about other exoplanets that one day we might be able to colonize and call our new home. So actually, one of the most common questions that I receive on the channel and on Facebook is to basically try to turn Jupiter into a star similar to our sun that you see in the back there, but then we can't. We can't for many reasons. And one of those reasons is because I think people that often ask this question don't realize how many Jupiters we need to combine together to create a star. So let's actually start by answering that question. How many of these do you need to combine into one large object to turn this into even the smallest star? We're going to create a new simulation, and in this simulation we're just going to start placing Jupiters right next to each other so they actually start colliding. So let's put a bunch. This is 5, this is 10, and let's wait for all of them to combine into one large mega Jupiter. If they start escaping, we can go into power and disable halt all velocities, basically. Once you halt all velocities, everything will combine into its one large object. So this is a Jupiter that's supposed to be about 10 masses of original Jupiter. It's unfortunately not as big, I think, because we lost a lot of the stuff to those collisions, but we're just going to cheat and make it 10 masses of Jupiter. So this is 10 Jupiters together. All right. How big is it compared to the original Jupiter? Not that much bigger, in terms of at least volume. So volume-wise, they're still relatively similar. Okay, let's hold all velocities again, and place 10 more Jupiters around the massive Jupiter, making this a double massive Jupiter. So hopefully this will now have 20 masses of Jupiter, but it doesn't, once again, because of the collisions. A lot of this material got dispersed into space. We might be able to recapture it by doing this. Let's see if it actually happens. So this is now supposed to be about 20 masses of Jupiter, and still just a gas giant. It's still not a star. And if I actually accelerate this, you can see that a lot of this material falls back into this massive object, increasing its mass quite dramatically, making it a little bit warmer than before, but still not as hot as it should be. We're gonna make this 20 masses, and there you go. We're gonna wait for it to cool down as well. It's sort of spinning on their own axes, but that's okay. And there you go. So this is our supermassive 20 masses of Jupiter. Okay, we're not done yet. This is still not even close to being a star. Let's place, I guess, 20 more? Yeah, let's do that. So here we go. 20 more Jupiters. Sudden explosions, really fast, a lot faster than I actually was hoping for, but that's okay. And hold all velocities, combine all of the material into one, and hopefully get, okay, it's 38 masses. We're gonna go for 40 masses of Jupiter. Very fastly spinning object, very interestingly looking, but once again still not a star. Even after 40 Jupiters, we're still not in a star formation mode. Let's put 20 more, making this 60. This time we're going to make this a little bit more dramatic. We're going to actually decrease time and just watch all of these supermassive Jupiters collide with the ultramassive Jupiter and possibly cause some bugs to the game as well. Yeah, they're not really doing so well. And they're actually colliding with one another as well, which is kind of interesting. But if I hold all velocities, they'll all start coming toward us. And eventually, hopefully, we'll combine into one massive object. So let's wait for this to happen, and by the end, we should have an object that's about 60 masses of Jupiter. Now, is it going to be a star? Well, let's see. Take a guess. What do you think? Do you think it will be a star? I am pretty sure it's not going to be a star, and you're going to find out why in a second. And there's that final suction of all of the matter, including the last object that we still haven't collided with. And at the end, we'll get a total mass of 60 Jupiters. Now, at this point, this is now classified as a brown dwarf. It's still not a star. It's a little bit more massive than a gas giant, but it does not have a nuclear reaction on the inside, so it's not technically a star-star. You can see it decreased in size because of its sudden increase in mass, and it's now even possibly smaller in volume than the actual Jupiter. If I were to compare this to our beautiful Jupiter, you can see that it's actually smaller in terms of size, but not in terms of mass. It's a lot more dense, that's why its volume is so much lower. Okay, so let's put 10 more, making this 70. There is the 70 Jupiters, and once they combine into one, which will hopefully happen once all of these bugs are resolved here. I think something got stuck on the inside, but anyway, once they all combine, we should have a total mass of close to 70 Jupiters. And this might initiate the nuclear reaction. If everything goes right, we might be able to create a star. And looks like we lost some mass again. We need to try to regain that mass by reabsorbing it, by halting all velocities again. And at the end, this will hopefully become a star of some sort. So we're currently at 53, 55, 60 masses of Jupiter. It's increasing dramatically. And will this become a star? We're very, very close to 70 masses of Jupiter now. We're absorbing more and more matter as it sort of orbits around us. And at this point, maybe, just maybe, nothing. Still nothing. We're over 70 masses of Jupiter and we're still not a star. So this really kind of shows you how much more massive our Jupiter would have to be before it actually turned into a star. Okay, let's go to 75. We're going to start placing them one by one. Here goes one. It's slowly being eaten away by this object in a very interesting manner. And I think it's actually losing a lot of the mass too. I don't know what's happening to that mass, but it's definitely disappearing somewhere. And this is 75 masses in total. Once everything is absorbed, we should have some kind of a indication whether this is still a brown dwarf or a star. Right now, it's kind of hard to tell. And here we go. This is 75. And we're still a brown dwarf. We may need to go to even a higher mass, because this is still a brown dwarf. As you can see, it's shrinking in size because its density is increasing quite dramatically, and it's basically a very, very, very compact gas giant-like object that is technically known as a brown dwarf. We might need to get 5 more going. But what's interesting though is that this object is actually now a lot hotter than a typical gas giant would be. So its temperature is about 1400 degrees Celsius, and it seems to be stuck at that temperature. So in other words, it actually radiates quite a lot of heat, and you could potentially even have habitable planets around it, or in this case, I guess it would be habitable moons. Okay, we might need to place a few more Jupiters for it to turn into an actual star. We're gonna start with 1. Or actually, let's put 2 at a time. So this is 77, and this will be 80. So let's see if we can now maybe officially turn this into a star by placing 80 Jupiters into 1. And so here goes nothing. This is now going to be a very, very massive object once it combines all of the mass into 1. And any second now, let's see what happens to this. It's still just a brown dwarf. 60, 70, 75, and still absorbing some of the mass. It's sort of jumping out because of all of the collisions. And there we go. There is that star at 78 masses of Jupiter. Now, that's just a red dwarf. It's a star that is very, very, very small in comparison to our sun. Very similar to the recently discovered TRAPPIST-1. It's also a very active star, so it's very unlikely that we would find any habitable planets around it, but it's not that much bigger than Jupiter. But what this should have showed you is how difficult it is actually to turn a gas giant into a star. You need 78 Jupiters for us to have another star in our solar system. So if I actually go back to our solar system and look at our Jupiter, I need to increase its mass 78 times for it to actually turn into a star. This would be quite impossible for two reasons. One is that a total mass outside of our sun, basically if I were to collect all of the materials outside of our sun, planets, asteroids, ice, comets, all of the moons, everything together, it wouldn't even give us 2 Jupiters in total. To get 78, we need to get a lot of stuff from somewhere. Maybe it's 79. Is it 79? Yes, it's 79. We need to get a lot of stuff somewhere else from the outside of solar system. Where that's going to happen, we don't really know, but essentially it's quite impossible to turn Jupiter into another star. But it would be fun to have one though, and we would then become a binary solar system. And if I look at Earth now, its temperature would actually start increasing quite dramatically, because now we have 2 stars on opposite sides of our planet. One very dim red giant that's right there somewhere, that's illuminating our dark side, and one, our regular star, the Sun. So this also means that with time, the temperature on planet Earth will actually become much hotter than it currently is. And there is the red dwarf Jupiter that's illuminating us from the outside. I'm going to run this for maybe a few months just to see how temperature changes and just to see what else happens in our solar system as the supermassive giant red dwarf star Jupiter starts causing all kinds of trouble here. And interestingly, the temperature on our planet hasn't actually changed that much, but the orbits are changing quite dramatically. And that's probably because Jupiter is slowly Jupiter, the star that is slowly stretching all of the orbits of inner planets, making them a lot more elliptical, including, of course, our planet Earth, which is now going to have a slightly different orbit from before. And anyway, so that's all I wanted to show you in this video. I wanted to experiment with Jupiter, turn it into a star, explain to you why it's actually kind of impossible in practically speaking, and also give you an idea of what would happen if Jupiter did become a star. So this binary system now has 2 stars orbiting around one another. And this is actually based on a completely new study from 2017 by John Chambers, a researcher at Carnegie Institution for Science in Washington, D.C. And he actually analyzed the creation of various gas giants and used various simulations and different models to try to predict what they used to be like and what actually happened on those gas giants early on in the beginning of the solar system. So let's actually visualize all of this by creating a brand new and very, very young solar system with the sun in the middle and the accretion disk that then will turn into planets and various asteroids with time. So you can kind of see that there's these chunks of asteroids here. I didn't really make them specifically any size because I just wanted to help you visualize what actually happens. So somewhere at a distance of several astronomical units, this is where Jupiter started to accrete and basically started to become a larger and larger rock that eventually would dominate all of the other rocks. Here we're going to represent this with a randomly generated rocky planet at a distance of about, let's just say 7, or maybe, yeah, let's just say 7 astronomical units right there. So this is going to be our Jupiter. This is kind of what it looks like. And basically it's a combination of, I guess, rocks and also water. So there's water and rocks here. But the thing is, at some point, when it reaches the mass of about 7 moons, and as it accretes more and more mass, it's actually going to acquire just enough pressure and just enough amount of material to start kind of emitting some of this ice water, which will eventually result in something really interesting. It will actually start basically subliming and creating water atmosphere. So this water atmosphere is what will actually turn us into a water world. And we're going to simulate this by adding atmosphere right now, and by basically changing some of the parameters until the Jupiter starts getting liquid water. So the atmospheric pressure here will start growing larger and larger because more and more ices fall onto the planet. the pressure inside of this planet starts to melt the ice and liquefies it. And then, because there's no other air present here, water and a lot of other liquids that might be on the surface start sublimating and creating atmosphere that's mostly water vapor. And water vapor is a very, very, very potent greenhouse gas. So it starts warming up this planet quite dramatically. And you'll notice that the surface temperature here is basically skyrocketing because the surface pressure has increased so much. So as this happens, this planet will start transforming, and it starts transforming relatively quickly actually. This only takes it about a few million years. And then for the next few million years, as it grows more and more, bigger and bigger, and more massive, it acquires more mass, it acquires more ice, it acquires more atmosphere, and starts creating this very, very beautiful liquid world of basically water. Now, this is what Jupiter was like for at least a few 100,000 years and possibly even a few million years. It basically was a liquid world. And even though it was relatively far from our sun, it was basically acquiring mass and water and pressure for maintaining this atmosphere from all of these particles that you see orbiting around it. So basically it was absorbing the accretion disk material. But what's interesting here is that its mass was far from even the mass of Earth. As a matter of fact, the mass where it started doing this was only about 0.1 or even 0.04 or about 8% of mass of Earth. And as the mass increased, obviously the other parameters increased as well. But it probably maintained this state for quite a long time, possibly even until it reached about 2 to maybe 5 masses of Earth. And when that happens, this is when it starts transforming. So basically, up until about 2 masses of Earth, it's going to maintain its habitable state. So in this case, it kind of froze over because I believe our atmosphere decreased a little bit. But we can return it back to the habitable state by increasing the atmosphere. But so yeah, at this point where it becomes really large, so maybe up to about 5 masses of Earth, this is where something starts happening and it starts changing into a gas giant. And it's mostly because the pressure inside is so great that the water is no longer liquid. As a matter of fact, it starts acting like a kind of a supercritical fluid. And on top of this, because the mass of this planet is so much larger now, it's basically at least 2 to possibly 5 masses of Earth, it starts attracting more and more and more mass from around itself. We can demonstrate this by launching a few random asteroids here. And as all of this starts happening, it starts growing exponentially. It basically starts acquiring so much mass, possibly not as many explosions would actually happen, but it basically starts vacuuming up the massive amounts of mass from nearby. And at this point, it starts absorbing things like hydrogen and helium, and so, ooh, that was too fast. And slowly, okay, let's do this slowly. Slowly, didn't work. Slowly transforms into a gas giant. And the more mass it has, the more stuff it absorbs. And this is going to keep going until it reaches the mass of about 318 masses of Earth, which is the mass of Jupiter as we know it. Now, this process was obviously not super fast, but it was a process that occurred in 4 objects in our solar system, and possibly even 5, because there is a hypothesis that I spoke about previously that suggests there was a 5th gas giant. But anyway, so this is what we think happened to our Jupiter, and notice how we actually were able to create Jupiter with an actual eye of Jupiter, or I guess a great red spot of Jupiter, completely by accident. And so now this is a well-developed gas giant as we know it today. And some of the other materials that orbited with Jupiter basically became its moons. So this is how the moons of Jupiter were formed. And it actually ended up swallowing quite a lot of those moons early on. But the ones that survived stayed with it until today. Well, that's kind of all I wanted to discuss in this video, because I thought it was a really important new finding, and it kind of gives us a new understanding of how solar system was formed in the beginning, and actually creates a new possibility that maybe, just maybe, life in our solar system actually did start on these gas giants, and then somehow, through what's known as panspermia, managed to be transferred to other planets, including Earth. Those are obviously speculations, but you never know. And so here we are in Universe Unbox 2, and we're going to try to actually turn Jupiter, Saturn, and possibly Neptune and Uranus into Chthonian planets. But the way we'll do this is, well, one way of doing this is how we did in the previous video, by basically placing each of them individually very close to the star, the sun, and by basically burning away their atmosphere, their hydrogen. This is maybe not close enough yet, so let's actually do it a little bit closer. And so here we go. It's getting hotter and hotter. It's very close to the sun, and it's going to start losing its hydrogen shell any second now. But you'll notice that Jupiter doesn't actually lose very much. As a matter of fact, it's losing like milligrams per second, and that's because of its really strong magnetic field, which you can kind of see right here. So magnetic field does protect planets from losing material, and if you remove this right now, it will start losing material really fast, but still not fast enough. As a matter of fact, I would have to actually wait a few months, real life time, not game time, real life time, for it to actually lose everything completely. So I'm going to cheat a little bit, and I'm going to just look at the composition here, and you'll notice that we actually speculate that there's anywhere between like 6 to possibly 45 masses of silicates on the inside, but we're going to go with a game value of 6.38, and we're just going to essentially remove all of the hydrogen from this planet, and then change this mass to 6.38. That's kind of cheating, I guess, but you know what? Just for Jupiter, this would actually take really long time for us to turn into a true Chthonian planet. For other planets, however, we can actually easily do this, because if I were to place Saturn here now, and let's actually place Jupiter a little bit farther away now, possibly somewhere close to Mars, and go to our next planet of Saturn and do the same with Saturn. And if I were to do the same with Saturn now, you would notice that it actually starts losing its mass a lot faster, because its total mass is not as high as Jupiter, and because its actual magnetic field is much lower as well. So we're going to do this to each of these planets, and then we're going to basically place them in the region around our true solar system, so somewhere between Earth and possibly Mars. And what I'm going to do at the end, or close to the end, is try to terraform them and see what they look like. So Saturn is next, and here for Saturn, this would also actually take quite a long while, so there will be quite a long wait, so we may have to cheat here as well, because even after waiting a few minutes, this hasn't actually decreased much, but it would decrease if you were to place this around a much hotter or a much more massive star. Like, for example, if I were to do the same with Sirius, Saturn will lose its atmosphere a lot quicker. And so we're just going to use the same technique to change it into a Chthonian planet, and now place it a little bit farther away, let's just say at a distance of approximately 2.5 astronomical units. Now Uranus is next, and you'll notice that Uranus has a slightly different composition. As a matter of fact, Uranus and Neptune are known as ice giants because they actually have a lot of carbon-based compounds on the inside, and not as much hydrogen and not as much helium. So these two will actually have a very different composition by the time they're done burning out their hydrogen shell. So even though there's not a lot of hydrogen here, there's definitely going to be a lot of other stuff, like, for example, carbon dioxide and methane and so on and so forth. So various compounds that have carbon in them. And whether those compounds actually do get burned by the sun and get dissipated into the atmosphere, or if they stay on the planet, is something we don't really know just yet. But I'm going to assume that they're going to stay because they are heavier than hydrogen and helium. And so for the solar winds to shoot them out, to essentially to strip the planet of those materials, would be a lot more difficult. So it might happen, but it might happen really slowly. So we're just going to leave them on Uranus and Neptune and keep them where they are right now. And Neptune is the last here. Let's just place it back to where it was, or a little bit closer than where it was before, at a distance of approximately 3 astronomical units. And let's take a look at what we've created. So we now have a completely different solar system with not 1, not 2, but something like 7 different terrestrial planets, or at least planets that might be habitable. So we have, obviously, we have Mercury and Venus, then we have Earth, Mars, and right before Mars, or right between Mars and Earth, we have Jupiter. Now it's still a little bit too hot here, and that's because I think it didn't cool down yet. We're going to manually cool it down, and let's zoom into it and see what it looks like. So essentially, this is the Chthonian Jupiter, a Jupiter that has no gas, or specifically hydrogen and helium atmosphere, and this is what it would kind of look like. Not very hospitable, not very pretty looking, but we can make it prettier and make it more hospitable by adding a little bit of atmosphere to it. And here, let's just give it Earth atmosphere, and also adding a little bit of water. I'm going to throw some water in there and make it slightly better looking than what it is right now. And here's some water on the surface here. It's unfortunately still ice, but that's because it's still a little bit too cold here. And we can change that by, well, let's actually move it a little bit closer to the sun. We're going to move it to a distance of about 1.2 astronomical units, a little bit closer to Earth, and obviously a little bit closer to the sun as well. And so total temperature here should be about 10 degrees Celsius, and it's going to start warming up any second now. And you'll see that it now has both atmosphere and also liquid water. Now, one thing I just noticed about Jupiter is that it's spinning ridiculously fast. Now, this is in 30 seconds per second, and look how fast it's spinning. In its current rotational period is something like 15 minutes. Yeah, it takes 15 minutes to rotate once. That's 1 day in 15 minutes. That's way, way too fast. We're going to just change that to something a little bit more manageable and make it stop spinning so fast. And there we go. So it's now a little bit more hospitable. It will now also increase its temperature. The water is melting, and you can kind of see that it's looking better and better. But still not a very beautiful planet, but nevertheless, this is a Jupiter that we can kind of live on now. And the mass here is about 6.4 masses of Earth, and total gravity here would be about twice as more powerful as it is on Earth, so you would actually feel twice more squished and would be able to only jump about half as far as you are on Earth. But this is Chthonian Jupiter. Next on the list is, of course, Chthonian Saturn. We're going to change its rotation speed as well. It's still a little bit too hot, but it's cooling down dramatically. It is going to be a little bit too cold here, so we may have to place it closer to... let's place it a little bit closer to the sun as well, at a distance of about 1.1 astronomical units. Get a little bit brighter here. And we'll now also give it atmosphere of about 1 atmosphere in total. And of course, give it a little bit of water. But look at that, there's actually water here already. So it looks like in a few seconds, this will become some sort of a water world. And yep, there we go. It's going to become completely and totally a water bowl. It's going to be a world filled with oceans, very, very deep oceans, and nothing else on it, not even a single island. So here, if we were to actually live here, and suddenly it's become a nice planet. Well, that's interesting. But yes, so here, if we were to live on this planet, a Chthonian world of Saturn, we would either need to bring a lot of different ships and vessels that can swim in the water, or live on a much colder ice planet that's covered in ice sheets of water. So that's Saturn, and next is Uranus. And Uranus is going to get placed a little bit closer as well. We're going to go into motion and slow down its spin. And now let's just cool it down manually and look at what happens here. So this world, or this planet, also has quite a lot of different water. And as a matter of fact, it has more water per volume than Saturn did. And all of this will turn into an ice world as well. And now I wonder if this is going to actually freeze over afterwards. Chances are it might actually freeze as well, or stay as a water world. We'll just run a few more. There we go. It has become an ice world as well. So the water has frozen. So we can basically either turn this into an ice world or a water world by increasing the temperature and moving it a little bit closer to the sun. And the last on the list is Neptune, and I have a feeling Neptune is going to be just very, very similar to these other objects that we just looked at. So as soon as you change the atmosphere here and decrease the temperature to something more manageable, it will very likely become an ice world as well. And actually, look at the really cool looking, almost like vein-like structures on the surface of Neptune. These are obviously randomly generated, but it would be really awesome if they actually existed in real life as well. And so anyway, so here comes the water world, and here comes the ice age for Neptune. It has now become an ice world. So even if we were to create Chthonian planets in our solar system, it seems that really only Jupiter is the only sort of planet where we can kind of survive on. So if Jupiter were to become a Chthonian planet, this would be the only world where we can kind of terraform it to look something like Earth. But the only difference here is, of course, the fact that the gravity here would be much higher than Earth. So we would have to create some sort of a gravity generator so that it's more comfortable to live here. But all in all, this is what these planets would look like. So this is Jupiter. This right here is Saturn, and it's sort of somewhere between ice world and water world, with a total mass of about 2.8 masses of Earth, so with slightly higher gravity as well. And I guess swimming here would be a lot more difficult as well. Then we have Uranus with a total mass of about 13.5 masses of Earth, so here the gravity is much higher, even higher than on Chthonian Saturn, and the surface gravity here is about 18.5 meters per second square, which is twice as high as it is on Earth. And then we have Neptune with the highest surface gravity of all of the Chthonian worlds, and this is essentially an ice world where once you land, it will be very difficult to walk, and you'll probably start sinking into the ice and the snow because of the high gravity. And let's look at all of these planets in the chart formation here. So here you go: Neptune, Uranus, Jupiter, Saturn, and of course Earth, Venus, Mars, and Mercury. So this is essentially what would happen if all of our gas giants became Chthonian planets. So in this simulation, what you can see is basically Jupiter right here, and these blue and reddish particles, which represent various types of asteroids and various types of essentially minor planets, orbiting like with it on the same orbit. They're essentially relatively large. They're anywhere between 1 kilometer and a few hundred kilometers. And if you look at them from the top here, especially if I just focus on the sun, you'll notice that they basically kind of follow Jupiter in its orbit without really going off anywhere. And as a matter of fact, this is a very, very stable orbit, and they'll stay in this orbit for several billion years unless something major disrupts them. Now, these are known as Trojans, and these are essentially types of positions in orbit where you can occupy a completely stable orbit and the same area as a main body. So what I mean by this is we have Sun in the middle, we have Jupiter orbiting around the Sun, and we have these much, much smaller objects attached to the so-called barycenter between the Sun and Jupiter, which I'm going to create right now. And what they're doing is they're actually orbiting this barycenter right here that's located just a little bit away from the center of the Sun. Now, this actually happens to various three-body systems, and so in this case, it's a three-body simulation. We have much more massive body, the medium-sized body, and very small body. Now, in this particular situation, these Trojans are very well known. As a matter of fact, there's like millions of them here, possibly just as many objects in this system as there are asteroids in the asteroid belt. And so we've already discovered about 6,000 of them, and they're all named after Greek or Trojan warriors from Greek and Trojan mythology. And like the famous ones are actually surprisingly two named as 617 Patroclus and a Trojan named 624 Hector, because they were accidentally put in the wrong camps. They should be in the opposite camps of each other, but that's not really important. What's important is that there's just so many of them that we had to use mythology to start naming these objects. Now, this is Jupiter's Trojans, and these are the most famous in our solar system. And before I continue talking about other types of Trojans, I just wanted to show you this picture right here. And this is essentially, these are the 2 points where they're orbiting. These are called L4 and L5 Lagrangian points, the points of stable orbits between various objects. Now, all of those orbits, all of those Lagrangian points can actually create stable orbits. We've actually made various satellites and placed them in various Lagrange points in between Earth and Sun 3-point systems. So if you actually ever search for various Lagrangian satellites, you'll find that, for example, there is a satellite located right here in front of Earth that's responsible for various weather measurements, and it's in a very stable orbit between Sun and Earth. But anyway, so the L4 and L5 Lagrangian points are very important because they're actually super stable. And they're kind of like about 60 degrees in between Sun-Jupiter lines. So like there's a bunch of them here and there's a bunch of them here, but it's not precise because they can still orbit the barycenter at various other locations. The L4 camp that's right here, that's the Greek camp, and L5 that's behind Jupiter, this is the Trojan camp. And as a rule of thumb, you can usually have Trojan satellites or Trojan minor planets whenever the system contains a very large object, for example, maybe something like 10,000 times the mass of the actual Trojan. And the secondary object is about at least 100 masses of the primary object. So basically, if this is like 10,000 masses, this is 100 masses, and this is 1 mass, then you will always have a very, very stable Trojan system with nothing crashing into anything else, unless, of course, disrupted by something passing through the system. And not surprisingly, other objects in our solar system have them as well. And let's actually start with the ones that are a little bit less popular. Now, you won't really see them in the simulation, but there is at least one Venus Trojan we've discovered. And it might be a little bit unstable, it might actually disappear one day, but it's been discovered in 2013 and it's known as 2013 ND5. It's a temporary Venus object that's somewhere right here. We don't really have it in the simulation, unfortunately. There's also Earth Trojans, and these were discovered and announced back in 2010, 2011. And the one that we are certain about is known as 2010 TK7, also somewhere right here. This was announced by NASA about 7 years from when I'm making this video, so it's a very recent announcement, and we actually expect to find more as well. There are at least 4 Martian Trojans known, and these are located both in front and behind Mars. And we actually have a few unconfirmed Trojans for Mars as well. And these very likely were captured asteroids from the asteroid belt, and then basically assumed the orbit where Mars, Sun, and the Trojans form a kind of a stable 3-body simulation. There's also at least 17 Neptunian Trojans, and we actually think today that Neptune probably has a lot more large Trojans than Jupiter does because it's capturing all these objects from the Kuiper belt. There is also at least one object we found orbiting with Uranus. This is known as 2011 QF99, and this was located back in 2013. And the second one was actually very recently announced in 2017, so there's at least 2 we have now discovered for sure, and possibly more coming in the future. Now, one planet that doesn't actually seem to have any Trojans is Saturn, and there's actually a kind of a mathematical explanation to it. It's basically because Jupiter is stealing all of Saturn's Trojans, and it's just too far away from both the asteroid belt and the Kuiper's belt to attract its own. So Saturn actually has very different Trojans on the inside of its system. We're going to talk about this in a second, but it doesn't have anything in its L4, L5 orbits, and at least we haven't discovered anything. And if it did have anything, Jupiter would have stolen it already. Now, even Ceres and Vesta have Trojans as well, but they're not really stable. But both of these, so this is actually a dwarf planet, and this is an asteroid, very large asteroid. Both of these have their own Trojans in the asteroid belt, but they often kind of exchange them, and they often change as well. And we even think there's possibly somewhere out there in the solar... And we even think there might be something called Trojan planets, maybe not in our solar system, but it's very possible that you might actually have a planet located right here, which we can totally place right now. Let's place a little randomly generated rocky planet orbiting around the sun, and it's going to be roughly in a 60-degree angle from Earth. So somewhere right here, I guess. We're going to place it right there and see if it actually stays stable. And so this is a kind of a hypothetical concept where in some other solar systems there might be these Trojan planets located in the same region as the main planet. Now, we haven't really discovered any, and there was one example we thought existed, but then it was proven to be just a glitch in data. But anyway, let's talk about other types of Trojans, and specifically here we're going to be going to Saturn now, which doesn't have its own Trojans, but it has what's known as Trojan moons, and I'm gonna try to show them to you right now. So within the Saturn system, and this is actually the only system we have that has Trojan moons, there are basically moons orbiting in the same region, in the same orbit as the other moons, and specifically they're actually located in the Lagrange points L4 and L5 of the larger moon. So here, one example we have, let's actually look for it, is Tethys, which is the larger moon with a size of about 533 kilometers, actually has two of its Trojans. Now, one is surprisingly close. This is actually a mistake in the simulation. So one is here, Telesto, and one is right there, Calypso. Now, both of these are the Trojan moons of Tethys, and they're much smaller than Tethys, about 50th of the size, or at least mass that is, and Tethys is obviously much smaller than Saturn. And the second Trojan moon triplet is Dione, being the main moon, so here it's about 560 kilometers in size, and it has Pleuduces, which is about only 1.3 kilometers, and Helene, which is right there, which is also about 17 kilometers in size. Now, once again, they're not exactly in the right positions in the simulation, so they'll unfortunately start losing orbit, but in reality, they're located in L4 and L5 Lagrangian points. So basically, this kind of gives you an idea that there's a lot of various possibilities for Trojan-like orbits, for L4, L5 orbits. If you have a very massive body in the middle, slightly more massive body orbiting around it, and then even smaller bodies in these L4 and L5 points. Hypothetically, or I guess in real life, if I were to run the simulation for like billions of years, these triplet moons would stay in stable orbits forever. But because here they're actually kind of a little bit off, they might start flying in different formations with time. So let's actually start by adding Jupiter to the system. Why? Well, because I want to actually show you the comparison between the size of the TRAPPIST-1 system and the system of the biggest gas giant in our own solar system. We're actually going to place it a little bit maybe farther away, just so that we can create a stable system here. And so there is Jupiter, there is TRAPPIST. And so now let's go in here and click on the action of adding moons to the planet. And look at that. Look at the size of Jupiter in comparison to TRAPPIST. It might be hard to tell, but if I were to actually add orbits here, you would see that in terms of size, basically TRAPPIST is even a little bit smaller than the Jupiter system. Now, it doesn't mean that it is smaller, because it's very likely that there's a lot of smaller objects that we haven't detected around TRAPPIST system. Like there might be smaller planets, smaller planetoids, and dwarf planets orbiting around it, far away from the location of even TRAPPIST-1H. But in terms of the actual size of the bigger moons of Jupiter, so there is TRAPPIST, with the farthest planet being at a distance of about 9.4 million kilometers. And here is the system of Jupiter with its Galilean moons. And the farthest moon of Jupiter, Callisto, is at a distance of about close to about 2 million kilometers. So in other words, the system of Jupiter is just a few times smaller in terms of radius in compared to TRAPPIST, but when it comes to actual size of the planet versus the star, this is Jupiter, and this right here is TRAPPIST. So it's actually just a little bit smaller than TRAPPIST itself. So Jupiter system is a very good representation of what TRAPPIST looks like. This, of course, applies to other red dwarfs as well. Let's actually do this again for another really famous red dwarf, the closest neighbor to us, Proxima Centauri, with its excellent, beautiful Earth-like exoplanet known as Proxima b. If I were to place Jupiter here again and give it all of its moons one more time, you can actually see that the distance between Proxima b and Proxima Centauri is once again not that far off from a distance to the farthest moon of Jupiter. So here the distance is about 2 million kilometers, and here the distance between Proxima b and Proxima Centauri is only about 7.2 million kilometers. So maybe in terms of radius, it's about just over 3 times larger. And how big is Proxima Centauri compared to Jupiter? Well, let's go there and check it out. So there is Jupiter, and here is Proxima Centauri, which is once again just a little bit bigger than Jupiter. So a lot of red dwarfs in our galaxy, and there's actually close to about 90% of all of the stars that are red dwarfs, will be very, very, very similar to Jupiter. And they will actually reflect Jupiter in many different ways, including the fact that many of the moons will be tidally locked, or I guess planets around those red dwarfs will be tidally locked. Many of them will also exhibit very similar other orbital parameters, and also very likely be affected by their parent star in the same way that the moons of Jupiter are affected by it. For example, one of the biggest effects that Jupiter has on its moons is the super high radiation from its huge magnetosphere. Its magnetic field covers a very large area, and the moons of Jupiter are highly affected by it. Now, this might actually happen around these red dwarfs as well. So there's quite a lot of different effects that might prevent planets that orbit red dwarfs from basically having inhabitable planets, which doesn't really give us a lot of hope, unfortunately. And of course, if we go back home to our own sun, if we take a look at our own solar system, we can kind of realize pretty quickly that in comparison to all of this, TRAPPIST system is actually very, very, very tiny. So I've done this before where I basically placed it somewhere right here, and you would notice that even if I add all of the planets to TRAPPIST, they're so tiny, so insignificant. And there's actually one that just accidentally left the system. But yeah, they're so tiny and so small in comparison to our whole solar system. Which once again means that our sun and our solar system is very, very unique. Not only is our sun very calm compared to other stars, specifically red dwarfs, our sun also seems to have very unusual parameters for its system. It seems to have terrestrial planets on the inside. It seems to have gas giants on the outside, and it does seem to have very hospitable conditions for water and for essentially life on Earth to develop. We haven't really found a system just like it, and we'll probably still keep looking for a very long time. So even if I look at these nearest 400 stars, the newly added simulation in Universe Sandbox Square, even if I look at all of these stars in our neighborhood, it's very unlikely that most of them will be as calm, as perfect for us to actually find a habitable planet around them. Stars like Barnard Star or Gliese 1214 or this one right here, Wolf 630A, will be red dwarfs. They will be too active, and they'll very likely have planets that are tidally locked to their stars. And other stars like, for example, this one here with a very difficult name of 9 Alp 2 Lib, or even more famous stars like Altair, that's actually right here, are possibly a little bit too large and a little bit too hot to have a habitable planet anywhere within its vicinity. But we don't really know just yet because we haven't really found anything interesting about Altair. Anyway, so that's all I wanted to say in this video, and hopefully now you know why our sun is so unique, and also why the variety of different red dwarfs that we discovered and all of the planets around them might not potentially be our future home. They're just not as good as our sun, unfortunately.
Hello wonderful person, this is Anton, and today we're going to go to Europa yet again, but this time we're going to explore the surface of Europa in the scenario from Take on Mars right here, Europa, the surface. Now, we did the ocean below last time, and it was supposed to take us about 30 minutes. It took us about 5. This one says it's an hour, So I'm guessing it's gonna take me about 10 minutes. So let's run through this. Let's see what we can actually discover. I don't really know what's going to be in this. I haven't really played through this yet, but here we go.
John Shepard to assess prospect sites 1 through 4 for sampling and analysis. Repeat, John Shepard to assess prospect sites 1 through 4 for sampling and analysis.
Looks like I'm up. Best take the buggy in the garage bay, or the aerial transport on the landing pad up top. Let's go prospecting.
So we're playing as John yet again. I don't know if Gus is here as well. He was in the last video. And we're going to be prospecting on Europa. So the surface of Europa, as you can see, has very low gravity, so we can jump really high, which actually is creating a bit of a problem for me to walk here, because if you run really fast, you start flying right away. It's a bit of a problem. Anyway, we're going to be getting our suit first. And he mentioned that there is actually an aerial buggy here we can use, which I would love to use. But first, let's actually suit up. Oh, okay. That's kind of what just happened. I don't know. Oh, here we go. So ooh, this is an interesting tool. We need to put a suit first. As you probably know, Europa has absolutely no atmosphere on it. So we need to have as much... Oh, drill sampling too. There we go. We need to have as much oxygen as we could get.
That looks like everything. Time to get going.
We have a drill tool here. This is meant for sampling. I think we're probably just looking for a place to essentially drill into Europa's ice shelf so that we can actually then send the submarine there, which is what we did in the last video. And there's 4 sites here. We're going to lock this up. Why are we alone? This is very interesting. What happened to Gus? Or where did Gus come from then? He was there in the last video. And I know I'm playing these out of order, but still, all these questions. Okay, so we have a buggy. And he did mention that there was something else here, right? Some sort of aerial thing. Okay, we can open the ramp. Oh, this is really awesome. Look at that. Jupiter is in the background. I love it. Very, very beautiful. So we can either take the buggy or the what again? This is what our base looks like. Whoa, getting disoriented a little bit. And just first impressions here. This looks absolutely marvelous. There's a sun in the background, very, very small, obviously, because we're so far away from it. We are on the surface of Europa. Jupiter is right there. One thing that I have to kind of mention before we start is that we're probably being bombarded by tremendously powerful radiation right now. As a matter of fact, we are not really in a safe situation right now. We need to have a lot of cover for us not to basically receive any fatal amounts of radiation. Now, I don't know if I can go up here. It looks like I can, but I'm having trouble climbing. So maybe the answer is no. Or actually, never mind. Oh, here we go. Oh, this is what he was talking about. That's the flying machine, whatever it was called, aerial something. Let's try to take that. I'm sure buggy is fun, but I would love to experience whatever this thing is. So how do we use this? It looks like a lunar lander. I'm sure it's going to be really complicated to use, but I cannot possibly not use this. This is going to be super fun. It's meant for 2 people. I guess there is definitely another astronaut somewhere. Okay, drive vehicle. Turn it on. Stats, map, land cam. Let's do land cam. Whoa. Okay. Okay. I just did something. I think I burned something. Anyway, let's fly this. Oh, here we go. Oh, that's cool. Wow, this is really awesome. A little bit more complicated than I thought it would be. But it looks like we're flying. This is amazing. Whoa, this is really cool. Look at the surface features here. Very beautiful. So we're going to site number 1. We're going to see what we can achieve there. And hopefully we'll have enough fuel to go to site number 2 as well. Okay, I think to land I just have to do nothing, right? I just have to like hold Oh no, I can also hold control button. Really cool. And we're gonna use the land cam to try to basically land right next to this site. Let's see if we can do it. Looks like a lot of this is actually automated, so I don't have to do anything. But I'm still having a bit of a trouble to land here. So let's see if we can just kind of slowly position ourselves so we can actually land. Here we go. Here we go. It's telling me to emergency eject. I don't like that. I don't want emergency eject just yet. I think I can do this. I'm so close. Come on. Look at this. Very close. Alright. Mission partially successful. Okay, that is not the best spot to land, but cool. Very, very cool. So I think we came from somewhere over there. Yeah, there's our base. So that was a pretty awesome way of getting here. Definitely not something you get to experience a lot, even on Mars. So here, I think I just need to take a sample of this, right? And it looks like that is it.
Time to move on to site 2.
Perfect. All right, done. Site number 2 is over there. So maybe we can take this thing again and bring it to site number 2. It is a little bit difficult to control, but I think it'll save me a lot of time if I do it this way. Basically, we just need to do this, right? And this. Yay, alright, I'm getting the hang of this. It's actually not as difficult as I initially thought. Whoa, I just think I saw a geyser right there. There's an ice eruption that just happened in this location. Now, I wonder if I should go check it out now. Oh, there it is. Look at that. This is beautiful. Definitely going to check this out as soon as we collect the samples here. So let's land again. I think I just have to basically crash land my craft and then click on standby button right here, and that's it. Right? Okay, that worked. So let's collect this really quickly. I really want to go check out that geyser because right now this is not too eventful. We're basically just collecting samples. But as soon as we're done here, we're gonna go see what's up there. So I think just to collect samples, I need to hold this for a few seconds. And now we're going to site number 3. I think I'm much better at controlling this thing now than I was before. And it's actually kind of fast. Now that I'm thinking about it, it's way faster than I thought it was. And it's like a really powerful helicopter. Lots of geysers showing up, so this is going to be exciting. Don't really know what we're going to find yet, but looks like we're going to be finding... Wait, what is that? There's something else there. Looks like we're going to be finding some kind of a mystery here, which is actually something that I didn't expect. I thought this was just a sample collection mission. Anyway, so we're going to very gently land here without destroying anything, hopefully. And stand by. Get out of the ship. Go quickly collect that sample, and I think there's only one left after this. And with this done, we only have one side left. And beautiful Jupiter in the background there. Let's get on there. Craft, turn it on, and head to the last site. I think we're actually going to be passing above the whatever that structure is right there. Oh, this is awesome. What is this thing? This is not where we're going actually, but I still wanted to see what it is. Oh, looks like... Whoa, this is beautiful. Look at that. We got it right in the geyser. Amazing. But yeah, looks like this is where the submarine is going to be most likely drilling and going inside the... underneath the crust. Underneath the ice shelf. Anyway, we are actually headed here, right? Yep. And... what is... This is a different type of ice. Definitely not the same as the one we just came from. So let's just land here. Wow, this is so beautiful. This is way more beautiful than I imagined it would be. Such a good job that they did here. Okay, so John clearly doesn't want to go in the crevice, but he has to. He has no choice but go into the crevice. Let's land on a harder surface here. And we're going right there. Let's just jump into it. Alright, this is kind of cool. I actually just realized I also get to slide on the ice if I'm going too fast. And I think Bohemia Interactive did an amazing job with some of the realistic aspects here. And you can also hear how John is actually a little bit stressed by my antics here. Me jumping around and doing all these crazy things is stressing him out, so he's not really happy about it. Anyway, let's collect this last part. I think this is actually very, very different sample, very different type of ice as well. So hopefully this will give us some kind of a new information. Alright, and that's it. Oh, I have to go back to the laboratory now. Okay, but before that, let's go see what that big thing was, because that's definitely something that is not mentioned in the mission. Let's go check out that whatever object that is. Okay. Music. Why is there music? Suddenly there's music. Interesting. I didn't expect that. I do want to actually take the flying thingamajiggy, but I can't seem to get to it. Here we go. And let's go take it for a ride again to the whatever that thing in the distance is. That object realism. I think there was actually 2 geysers that I saw in the distance, but I don't know what the second one is. And this is definitely a drill. I mean, at least it looks like it. It seemed to have been landed here, and it's probably going to be drilling into the ice shelf. I don't think there's an entrance here. I don't know if there is one. This actually kind of looks like the SpaceX landing module from this angle. Okay, so there is a staircase though. Can we take it? Can I use this? I can just jump on it apparently. And this takes us somewhere, right? Oh, there's a cabin. Look at that. Was there a person inside? I think it was a person. Okay, I just fell down. I want to go check what this is. This is kind of interesting. And why can I not enter this? Oh yeah, there's a guy right there. That's Gus. That's the Gus from the second part. Hi Gus. Why are you just standing there again? I found him. I thought he wasn't here, but I guess he is here. Alright, so let's go check out this thing first. And I totally just became unconscious by jumping too much. That's not cool. Apparently you can totally pass out, and I just did. And look at that, I woke up right next to the geyser. That's exactly where I wanted to be. Okay, so I have to be careful. I have to make sure I don't damage myself. The geyser is coming out of this thing, so I wonder what happens if I stand right in the middle. Oh, this is so beautiful. Look at that. These effects are amazing. But it's not really doing anything. I don't think it's actually projectiling me anywhere. Okay, so that was cool. Not exactly what I wanted to do, but cool nonetheless. All right, let's go. Let's return back to our laboratory. Let's take the spacecraft again. Oh wait, is this? Did I lose this? Yeah, it looks like I just dropped it. So I'm gonna leave it here, staring at Jupiter. It's gonna stay there for the rest of the existence of this moon. Anyway, let's go to our craft. Hopefully I don't unconscious myself again. But it looks like it's actually pretty easy to fall down here, so that I need to be careful about this. Also, because of this, I'm stressing myself out, and my oxygen level is dropping a lot faster than before. And we're almost there though, so that's okay. You can do it. Come on, John. Just one more jump. One more mega jump. And land right in the seat. Come on, you can do it. And so close. Very close. Hey, what is that? Some sort of a battery, I think. So here we go. And let's do this. Okay, Gus, I guess I'll see you later. You don't want to talk to me, and you don't want to open the door for me. But we're just going to go and return the samples to the laboratory. This thing moves a lot faster than I actually thought it could. This is crazy fast. So fast, as a matter of fact, that I seem to have missed my laboratory. Let's come back to it. I hope I don't crash. And I totally just crashed. Okay then, so that's not cool. I could have finished this. I was almost there and I was a little bit impatient and I basically ended up crashing my craft and dying on the surface of Europa. First person to die on Europa, John Shepard. Anyway, let's play through this again. Let's see what actually happens at the end. Okay, so here we go. Very gently, very carefully approach the laboratory, and I can maybe even land on the roof here, where we actually took off from originally. There's a staircase inside the building that you can take to try to enter the building. So I'm gonna do just that, like a professional. Land right on the roof of the lab. We can do it. There we go. Very close. Come on. You can do it. 1, 2, and touchdown. Touchdown. There we go. Excellent. Amazing. Now let's hope that we don't fall down and break something. And we're basically just going inside this room, right? Yeah. I just have to flick the switch here. And this will, I believe, initiate the repressurization. And now I can probably go inside. Alright, awesome. So looks like I was able to finally sort of finish this. Let's see what we have to do here. It says return to the lab, return the samples, right? Where am I taking the samples to? Here. I'm still wearing the suit, but that's okay. And I guess that's going to be the end of the mission, unless there's another part. Access the laboratory, transfer the sample, analyze.
Analyzed. Nothing special here. There. Nothing remarkable.
Okay. Okay.
Just ice.
Just ice.
Still nothing particularly interesting, though it does have some inclusions. Better log it. John Shepard's log, entry 201. Specimen labeled 0416 contains nothing remarkable at first sight. However, some inclusions were detected. Hence, I am leaving it in the deep analysis spectrometer overnight for extensive testing. End of log.
All right.
I was really hoping to find at least something. No luck, I suppose. Perhaps this ball of ice is dead after all. Well, whatever. Time to hit the hay. I've been dealing with the greenhouse plants most of the day anyway.
Okay, looks like this is probably the end of the mission. I just have to return to bed. I'm gonna wear my suit because I feel a lot more comfortable in it. And oh wow, there's so many beds. There's only 2 people on the entire station though, and one of them is somewhere far away. All right, lie down and ZZZ. I guess that's it.
Needed that. Wonder what the
John Shepard, report to the garage bay immediately. Repeat, John Shepard, report to the garage bay immediately.
Huh? Sounds serious. Better get there pronto.
Okay, so it looks like this was not the end. I spoke too soon. How do I get out of here? I forgot where the door was. Oh, here it was. All right, so it looks like there is some sort of an emergency. And I think it's something to do with Gus. He's probably going to tell us to get into the submarine, and this is how the part 2 begins, right? I'm just guessing here. I think I need to go... downstairs here, right? There we go. The garage is this way. And very disorienting, but that's probably because the game is still in early development. It's been in early development for several years, actually. So I don't know why it's taking them so long. Probably because they don't expect to make a lot of money from this. This is a very, very niche kind of a game. Only some people will actually enjoy this. Alright, so we're going to the garage. I'm guessing aliens, but probably not. I think it's Gus. I'm guessing it's Gus. Let's see what it is. Oh, you scared me. It is Gus.
Oh, hey, Gus.
No time to chit-chat, John. Hop in and drive. I'll explain on the way.
Roger that.
Alright. Oh no. I don't...
Switch this to a private channel. John, take us over to Deep Drill Site 04. I'll update you on the situation. First off, those samples you recovered, are they real?
Huh? What do you mean? Of course they're real.
You sure?
Yes, Gus, of course I'm sure. I bloody drilled the samples myself. They were completely contained from drill site to analysis bay.
And it's true.
Gus, what the hell are you talking about?
John, we found life. Those inclusions in your sample contain microbial life. DNA structures like no other.
My God.
Yes, John. You know what this means for humanity. But don't worry about that now. We finished drilling through the ice yesterday. It's as predicted, an entire ocean beneath the ice. You and I, my friend, are lucky lads. We've been designated as Diver Team 1.
Does that mean we're going under?
Yes, under.
In the submarine?
That's right, in the submarine.
Woo!
Hey, cool it there, cowboy. Get us to the site alive first, yeah?
Yes. Yeah, got it. This is what I've been waiting for.
Me too, John. Me too.
Okay, awesome. So that's exactly what I thought it would be. This is the beginning of part 2 that we covered in the previous video. And I guess the harder part for me now is to actually get them there alive. Just like I mentioned, I need to get them there alive first. And I was not actually very successful with this buggy so far. This is 860 meters away. There's a very high chance I will not make it in the buggy. Why could we not take the helicopter? The air machine. Buggy sucks, really does. Unless I'm doing something wrong, but it always flips for me. Every single time I try to ride, because of the low gravity here and a lot of ice, it just kind of flips. So anyway, but basically, yeah, that's I guess how the second part starts. We just go inside the drill, and in the next part we end up in the submarine. Let me try to skip through this part so that you don't have to watch me pace myself 1 meter per second for the next 800 seconds. We're gonna try to get to the drill site alive though. And just like that, I flipped. Let's see if we can actually flip back. We might be able to flip back because there's actually a engine here, and no, that's the end. Anyway, so I think I'm just gonna stop this here because I think we know what happens afterwards. I might have one day finished the scenario, but it's just kind of annoying that it doesn't save anything. But I'm pretty sure we'll just go inside the thing and then we end up in the ocean below. Anyway, I'm sorry I couldn't finish this. If you do want to see the end, I'll post it at some point separately if they actually add another scenario that I would like to play through. For now though, it's just not worth playing through because it did take me an hour to get there, and it's just, this buggy really sucks. Anyway, so that's Take on Mars, a game that's been in development for a long time, but hopefully one day they'll finish it. Because it is kind of cool. It does have a lot of really cool, realistic scenarios. I'll see you guys tomorrow. Come back tomorrow to learn something else, and space out, and as always, bye-bye.